Zo, zo. 1, 2, 3. One, two, three.
Okay. So thank you. Good morning, everyone. Today it's my pleasure to introduce you to couple electric magnetic dipole.gl, which is a Julia package for making multipolized scattering calculation in physics. And I want to start with this picture, which is the city where I live and where I work, which is Fribourg in Switzerland. And the city is famous for its bad weather condition. And why do I show you this picture is because it's interesting for me and for my group, because what's happened on this picture is that light from the sun gets scattered by the small water droplets in the cloud. And this is what makes the cloud to be white and also the image a bit blurry. And in my group, in Fribourg, the soft matter and photonics group, we are interested in this kind of system, but also in other things like structural colors. This is why this butterfly is blue. This is not because of the pigment in the materials that makes the butterfly, but because of the structure of the material itself. And also we're interested in nanophotonics, so interaction of light with nanoparticle. And before I continue, I should just acknowledge 3 collaborators that works on me on this package, which is Frank Scheffel, Diego Romero, and Luis Frufe. And so we are interested in light scattering, and I'm a theoretician, so I want to do simulation. And a method we can use to do this kind of simulation is the discrete dipole approximation, or DDA. And the idea of the DDA is that if you have an object like this sphere and you send light on top of it, and you want to know how light is scattered by this object, what you can do is you can discretize it in small cubes, like here. And what's nice is that you know more or less how the cube is behaving optically speaking. And it behaves like a dipole, electric dipole. So if you apply light, so an electric field on top of this, you will induce a dipole moment P in the cube, which is given by the polarizability alpha and the field you apply on it. And on the other hand, this electric dipole, it oscillates at its own frequency, and then it emits an electric field that follows this pattern here on the animation, and which is given by the green tensor here. That we see is like a coupling parameter later times the dipole moment. And so the method, if you have all your small cubes that behave like dipoles, the idea is that you couple them in this way. So I will try to explain it with the logo of the library. Each green dot here corresponds to one cube, and the idea is that you say that the total electric field on each of these elements is the input field, so the red arrow, so the light you shine on your object, plus the contribution coming from all the other dipoles that has a purple arrow here. And so what you get here is you get a system of equations that you can solve it. Like you can solve by inverting a 3n by 3n matrix easily. So it's not very complicated. What's more complicated is to code all the utilities that you need to compute the green tensor, the polarizability. There is an extension of the method which is called the coupled electric and magnetic dipoles, so SEM I call it. And the idea of the SEM method is that if you have not a big object that you want to discretize, but a set of small particles, like a small sphere, you can model each of these spheres with an electric and a magnetic dipole. So you model it with only one point. And then with this, you can get a similar, so you add a magnetic dipole, so you get a similar system of equation, which is a bit bigger. And to solve it, you just need to invert a 6n by 6n matrix. So this is another variant of the method. And these 2 methods, we implemented them in a coupled electric magnetic dipole.gl, which is a Julia package. And this is a collection of modules, Julia modules, organized around the central one, which is called DDA core, which is responsible for loading the system of equation and solving it. And around you have a lot of different modules like alpha for computing polarizability, input field for input field, geometries for making for discretizing some object. You have also some outputs module like post-processing is to compute physical quantity like scattering cross-section or local density of states, of optical states, and also a module for computing optical forces that are acting on the object. We have also some utilities module that are a bit lower level, but that are used in the others. And so these pictures come from a paper which is in review for publication in Computer Physics Communications, and I hope it will be published soon. So I will continue by showing you some example of what can we do with the package. The first is the light scattering by a polystyrene sphere. So if you consider one of this small polystyrene sphere, which have a radius of 230 nanometer, you can discretize it in small cube, as I showed before, and use the software to compute a property of this, like the differential scattering cross-sections that show you how much light is scattered in every direction, showing that for this wavelength, which is 4 times the radius, it scatters light mostly forward. Another example, now using the seventh method, is a Yagi-Uda antenna, a dielectric Yagi-Uda antenna. And for this, you probably know this type of antenna, Yagi-Uda antennas that have been used a lot, maybe last century. And the idea is that you can do it with small particles, with small silicon particles that are lower than 1 micrometer in size. So what you do is you put a big particle, the red one, which is a reflector, and then 10 directors in the direction in which you want to have the directivity. And so if you put a light source here, which is a dipole source, we can compute the emitted power by the antenna, and it shows that there is a huge directivity in the direction of the directors. So this is another application, and a bit more into research. This is results we published in Nature Communication beginning of the year, and we computed the optical forces, or more the optical binding between two polystyrene particles in a laser beam. So if you put two polystyrene particles in the laser beam, these two particles will scatter light, and the scatter light will introduce an interaction between the two particles that we call optical binding. And with the library, you can compute this kind of interaction, and here's a picture taken from the paper where the plane line has a simulation made with coupled electric magnetic dipoles, and the dot as the experiment that have been made in my group, and you see that it's agree pretty well. Okay, so I hope I gave you a good overview of what we can do with the software, and I will be glad to take your questions.
If I understand correctly, when you calculate the polystyrene sphere, you discretize it, and then sum up the results from all these dipoles. How many discrete points are you? How many discrete points are you discretizing it?
So I get a good result with 2,000 dipoles, I guess. I mean, there is a general rule that you should make it smaller than the wavelength of the field you input, like a couple of times smaller.
Right. So if you use less, you get a result that's not fully converged, and then you take more points, and at some point the result.
And in principle, it should converge. I mean, it's proved to converge into the good solution.
Let's thank our speaker again, and the next person can set up. Also, sorry, if you would like to ask a question, now that I have the microphone, just again raise your hand and I'll give you the mic so that people on the stream can hear the question too. Sorry.
Thanks everyone for being here. I'm really excited today to present this new package, Majoko.jl. And this was some work I did with a colleague, Nick Barber at the University of Sydney. So those of you might not know what Majoko is, so I'll just spend a few seconds explaining it. So Majoko is a physics sort of simulation engine. It also has a lot of tools built in for doing visualization as well. And its sort of primary focus is developing applications in robotics and for machine learning, particularly reinforcement learning. So Majoko is a pretty old project. It happened before we made the bindings for Julia. It's about 12 years old now, but it was recently bought by Google DeepMind, and they actually open sourced the project, which really helps us in making the bindings. And the reason we actually did this is because both Nick and I believe that Julia is a really good language for doing this sort of robotics and also reinforcement learning research, because you can really get at the high performance and you can be really productive and iterate quickly on your ideas. Now, what do we do with Majoko.jl? So what we do is we build the Majoko C library and we export the bindings into Julia and sort of make it quite ergonomic to use within Julia itself. And some of the work that Nick did was introducing a visualizer so that you can sort of develop your algorithm and see the results and play around in the visualization. Now we have to say there was a group called Lyceum that did a lot of this work sort of many years ago, and it's no longer maintained, but their visualizer, a lot of our code is directly based on their old code. So what I'm going to do is start a REPL session, because this is sort of the best way to show off the package. So the package is used like any other. You would install it with the standard Julia package manager. And if we want to visualize an object, what we have to do to start with is to load a model. And so the way we do that is with the load model function. And we load a specification. So Majoko environments are written in an XML specification that's all documented on their website. So what I'm loading is a cart pole model, which I will show in a visualizer in a second. So to actually run the visualization, we need an object to store all of the simulation data, like the positions and the velocities, which we create with this init data function. And now for the visualization, we don't install the visualizer by default on your system, just in case you don't want a huge number of dependencies. So instead, we have it in a package extension, and you need to call this function to be able to access the visualizer. So the way that we call the visualizer is just call model and just call the visualize function with a bang on the end, and this will launch an OpenGL window where you can play around with the visualization. And this is fully, let me just launch that again. This is fully interactive, so you can go around in the 3D environment and you can add forces to the bodies inside to see how they will react. Obviously this doesn't do anything for now, but what we'll do is write a very quick controller to move this green body to balance the pole vertically. And we'll do that next. So the reason why visualize has a bang on the end is because it changes this data object. And you can inspect something like the positions, and instead of giving you like a pointer to an array, we wrap it in a sort of Julia array that follows the abstract array interface. And if you didn't know what a property does, we have the showDocs function, which can give you documentation for a specific property of the struct. So this tells you it's just the position, and it tells you the dimensions of the array as well. So before we get started, I'm just going to reset everything to the default values. And now if I check the keypos array again, it's reset everything to 0. And to save a bit of time, I'm just going to copy and paste a function in. If you want to follow more closely, this is a guide in the documentation as well. So we don't need to understand this function, but I just want to point out a few key points. The model object is used just like you would a normal Julia struct, and you have access to all of the properties there. You also have access to all of the functions inside Majoko itself. So this MJD transition function is exported by Majoko, but we've wrapped it to make it a bit more ergonomic to use. One thing you will notice is we're initializing some arrays with this MJ zeros. This is basically just the zeros function, but it's a slightly different memory layout. I'll talk about that on the next slide. So when I say that we've sort of made it more ergonomic, one of the things is adding documentation to all of the functions. So you can see that this is a finite difference method to calculate some derivatives. And also, we tell you the input arrays, sort of what type they expect, and also the sizes as well, because these can be quite difficult to find out if you have to trawl through the documentation all the time, so you have access to everything in the REPL. So what I'll do is I'll continue creating the controller. So we need this K object. It's basically kind of like a spring constant, like a restoring force to try and keep the cart balanced. And to actually visualize this, we have to write a controller, which is just a function that takes model and data as input arguments and sets the control property of the data struct. So we can call this whatever we like. And inside, I'm going to construct the state by concatenating the position vector and the velocity vector together. And then I'm going to directly broadcast into the array, the control array, which sets the actuators with this value. And if we want to actually test this controller, we can call the same command again, model data, and pass in a controller, which is just the function that we've defined. So now we're running, and the mode has changed to controller. If we click play, nothing happens, but now when we add a force, the cart will balance itself from there. So we hope that you can use like the REPL to sort of create your controllers and iteratively develop them, tweak your parameters, and directly see the results. Okay, as promised, I'll talk a little bit about why we use MJ zeros. So under the hood, you're using C functions, and they take pointers to an array, which is linear in memory. Now, all of C and NumPy use row major indexing, which is a type of memory layout, whereas Julia uses column major. So if you have a linear array, it's actually mapped into different locations, even though they're the same sized arrays. So what we do is we give you these two functions, MJArray and MJ0, so you can create an array in this row major memory layout to pass into your Majoko functions. But Julia is quite nice and smart, and the type system will make you be able to access these row major arrays just like any other Julia array. So on the Julia side, you don't need to worry what the memory layout is, but you have to worry when you're passing them into these Majoko functions. So just quickly, I'll just go over the design philosophy. So we give you access to everything in the C library. There's over 300 functions here and lots of structs, and these structs have hundreds of properties. So we think documentation is really important. How do you actually sort of navigate around? How do you know what to use? So all the functions that we provide have doc strings, and we also give you some extra functions like show docs to actually inspect what the properties are as well. Because if you want to actually have a look at the properties, the documentation for a struct is a few hundred lines long, so this makes it easier to narrow down on what you're interested in. We also provide a bunch of validation checks as well. So the Majoko function we used in the previous example has some guardrails to make sure that the arrays you pass in are the right size, the right type, and also the right memory layout. And we'll give you warnings or errors to make sure that you're doing everything correctly. One thing that's really core to this is we want it to be used for robotics and reinforcement learning research, so making it high performance is really important. So we don't copy anything across the language barriers. We just directly give you the views into the memory itself as well. And we hope it's still pretty easy to use. And we have a lot of utility functions as well to make writing the code easier and cleaner, and you can find that in our documentation. Okay, with that, I want to finish up, say a huge thanks to everyone that helped. We had a lot of help from various people online giving us some pointers on how we actually did this. And I also need to thank the Infinity Group at the University of Nottingham, because they actually sponsored me to come here and talk to you. The QR code is for the slides in case I went a little bit fast in this talk, so you can access them afterwards. And it's also on the schedule as well. But yeah, that's everything. I'm happy to take any questions now or later. please.
So we unfortunately don't have time for questions, keeping with the schedule. So if you'd like to talk to the speaker later,
Ask me afterwards. That's fine.
And let's welcome our next speaker. We did finally get cards. So if you're speaking, yellow card means 5 minutes, red card means 1. And I'll hold up a number of fingers too. Also, just keep in mind they have the camera centered so that they show the speaker. So it's set up right now for the speaker to be standing.
So I guess I will sit.
Okay. Should we move the camera down then? Just so your head doesn't get cut out.
I also have to this one. So okay, here we are. Okay. So let's start. My talk is about what's new in Warner FVM.gl. So that's a kind of talk which kind of is based on the idea that I already gave a talk in 2020 on Warner FVM, and then I just I'm supposed to tell you what's new, but before I tell you what's in it anyway. Okay, so that's a package to solve coupled nonlinear systems of partial differential equation of reaction diffusion convection type. Ah, there are no slides? Wait a minute. Ah, that's me. So wait a minute, what's that? File output, enable presentation mode. So what's going on? So basically I have presentation mode on. That's normally what is going. Ah, no, it's okay. Yeah, okay. Okay. So that's, yeah. So Warner FVM.gl is my package. I have something new since 2020, and I tell you what's in there. It's a solver for coupled systems of PDEs on domains in 1D, 2D, 3D, which also can be just any geometry. And basically, I'm working with reaction diffusion convection equations, which have some storage terms under the time derivative, some reaction terms between the species in the system, and some fluxes, which also can be coupled, and some sources. So they can also depend on the solution. It's all nonlinear, but they can also depend on position and time as well. And also basically a notation for boundary conditions where I described them just also as nonlinear functions. It's some kind of coupled nonlinear Robber boundary conditions, if you want to put this way. And I'm using the 2-point Plugs finite volume method. So the idea is that I take my domain omega, I triangulate it using just creating a Delaunay triangulation. Then I can create the Warner cells, which then serve as control volumes, and then I can use the Gauss theorem in order to cast the integral over the divergence of the flux over the control volume into some surface integral over the fluxes with the neighboring control volume. And for the Laplace operator, for instance, I'm getting out this kind of finite difference equation which then is a discrete approximation and discretization of the continuous system. So and this can also work in 1D or in 3D. And for the whole system, I get a coupled nonlinear system of equations. So this is basically for the discrete implicit Euler time step. I have these nonlinear flux functions now, which basically replace the continuous flux by some finite difference flux expression, which can all be coupled or nonlinear. I have the erection rate terms and so on, and the geometry factors kind of coupling these things. And this is a nonlinear system where the number of unknowns is the number of species in the system times the number of nodes in the grid. And yeah, so that's a method which has nice physical properties like maximum principles, positivity of the solutions. If these are present in the continuous problem, also we can show some nice discrete thermodynamics like entropy production estimates and so on. And also some divergent disadvantages, in particular if you want to solve hyperbolic systems. It formally would work, but it's not very well. So in that case, you should use Trixie, which is focused on that kind of partial differential equation systems. So how does this look like in the API? So basically I can create a grid. I describe a flux function, as I said, a source function, and I describe the bounding condition. So I cramp this in here in the Pluto notebook cell, and then create a system, and then I can solve. And I can easily change the grid and solve this in 2D. And yeah, so you can see it. So I can get the solution in 2D, and also just so with the same physics, I can solve this also in 3D. And I can get just the visualization of the stuff in 3D, so with the same boundary conditions. Or I can change, okay, so that's a Pluto notebook, of course. I can change just one of the parameters, making this really nonlinear, and I get the solution of the nonlinear problem out of this. I can also make an error removing the const, which means I will get allocations in my hot assembly loop, so users want to kind of be careful with this. Okay, so what's behind? So storage of unknowns is just a dense or sparse matrix. I use Newton's method to solve nonlinear discrete systems. I avoid global sparsity detection by calculating local Jacobians and putting them together into the global sparse matrix by an extendable sparse package which I wrote. And yeah, and then, okay, solve linear systems. I'm using linear solve now, and we can also use ordinary diffec.gl in order to solve time-dependent problems. And also I have a multi-physics feature in there, which means I can have different species in different subdomains. Here, for instance, I can have 3 species, one coming in here, reacting with the second one, which is transported, and then reacting to the third one, which goes out there. And so I can solve this also, yeah. And I can, here I'm using the default solver. I just can switch to some solver from the ordinary diffix. So I can create from my system, I can create an ODE problem and use all kinds of ODE solvers for these PDEs. And this amazingly works also for 2D, 3D, and it's faster than my kind of default solver. I'm amazed by this ODE system package, and I can switch methods and so on. This all works quite well. Yeah. Okay, and I also have a couple of accompanying packages which I maintain together with my colleagues, like preprocessing, meshing. I have a package called Simplex Good Factory, which makes a simple way of describing discretizations, triangulations, for instance, in 2D. Oops, that's a syntax error here. And, oops, and should be, of course, like this. Okay, yeah. And I also maintain the triangulate.gl and detection.gl packages for meshing. Grid management I'm doing together with Christian Merdon mainly, who has also a sibling finite element package on the same kind of package ecosystem. And for post-processing, you have seen now a code which I called gridvisualize.gl in connection with the PlutoVista.gl, which basically enables 3D visualization in Pluto notebooks based on VTK.js, so making it in the moment faster than Maki. I hope at some point I can also use Maki for this. So it already works, so there's a Maki backend, but it's, yeah, so not completely perfect now in the Pluto notebooks in the moment. Okay, so what's new? Basically, I worked on since 2020. I really learned step by step things from the SciML ecosystem, and I tried to make my package compatible to this, like using linear solve, common solve interface, ordinary diffec.gl, you have seen this. The interface, I'm also using the recursive array tools.gl, so okay, sorry for the wrong markdown syntax here. I can have now discontinuous quantities with jump conditions at interfaces. I just working on preconditioning, like equation block precondition for these coupled systems. Some various model additions like outflow boundary conditions, edge reactions, different coordinate system, velocity field projections. Currently, I'm working on multi-threaded assembly, and also I have ideas how to couple now with modeling toolkit, which could describe me or create me my kind of callback functions for describing the system. Maybe even symbolic index interface.gl could work, I don't know. But modeling toolkit really works. A student of mine really made great efforts to couple some Python code to Julia with this kind of intermediate representation for modeling toolkit, so it can work, and I want to have this. Okay, and we are using this for semiconductor device simulation, solar cell modeling, electrochemical reactions, chemical reactors performance. So Roman Scherer is also at the JuliaCon. He uses this for modeling of flow battery cells, and I have collaborators on reactive mixtures in porous media, geothermal two-phase flows. And I'm also teaching advanced topics from scientific computing at TU Berlin, and a couple of the ideas behind this you can also find out in the course, which is online. So thank you very much.
So in the interest of time, I don't think we have time for questions. Again, if you'd like to ask the speaker anything, definitely find it during one of the breaks.
Sure.
Our next talk is actually a pre-recorded talk from one of our Quantum Mini Symposia sponsors, the Unitary Fund. So Roger is going to set up the talk, and I think we probably don't need to broadcast it like live. Is there an easy way for us to rebroadcast it on the stream? I don't think so, right? Okay, so we can watch the recorded talk, and we also probably won't be able to take questions on this one because it's recorded. And Nathan is in the U.S. and thus he's probably still asleep.
Yeah, if you have questions, you can also ask me later. I'm here all the time anyway. Is this the wire? Wait, is this the right wire?
Is it not?
Yeah, it's not. Well, my laptop detected, and not on the screen.
Did you like hit F5? You're on OS X, right?
Not sure what's happening. Displays. Maybe it's a laptop issue. I can.
It was there. It's only black sending out.
Yeah.
Okay, that looks good.
Maybe
it's not
maybe
popping
I'll
up in
switch.我这个坏了。Oh, okay.
It's always a nice reminder that you are this way really glad to be able to. Hi everyone. It's the first time I record the video this way. Really glad to be able to present. And sorry I cannot be there in person. My name is Nathan Shama. I am CTO at JuliaCon, and I'm really excited to present the work we've been doing toward nurturing a quantum open source ecosystem at JuliaCon. So let me give you an outline of this talk. Of course, I'll try to give a spotlight to Julia and Julia projects as much as possible. I will start by telling you what we do at JuliaCon, our scope, which encompasses Julia projects and has a lot of overlaps, but is also including projects and activities in other languages or that are not only in open source software. I will speak about the microgrant program. That is the way actually Military Fund activity started, and it's actually the main program that we have to support new projects in the community. I will give an example of a well-established project who is now exploring Julia, and then give more information about our meetings, our surveys, what we see in Open Harbor in quantum technology, our special kind of hackathons that support also Julia projects. And finally, I will speak about two open source projects that we develop in-house with our Military Fund team and a global community, of course. They are Metric, a platform to benchmark quantum computing resources, and Metic, which is a Python toolkit to mitigate errors coming from quantum computations. So first of all, well, in this setting, I don't need to make the case for it, but it's always a nice reminder that open source software needs some sort of support. It comes in various forms. We know where like companies, corporates, research institutions, but also targeted institutional support for open source software is crucial. And these three projects, which have a tremendous impact to the scientific community and beyond, have some kind of institutional organizations that help their growth and maintenance. So what Military Fund aims to do is, in a broader sense, the vision is to have a quantum computing and quantum technology ecosystem that helps the most people. And our mission finds that supporting open source software at this point where there is so much software to build, so much communities to grow, it's one of the most effective ways of doing so. We do three main things, to which I gave some hints of previously. One is the microgrant program, which I will tell you about. We've funded, with no strings attached, over 100 teams in 31 countries. I will give more details about that. Secondly, I spoke about the technical stuff, which I lead, and this is mostly the research we do in-house with and for open source projects. And finally, there are a broad range of community activities that we do with a global community of hobbyists, researchers, students, and software developers alike. So this is the Military Fund team. And I would really like to acknowledge all the folks on the team. Purva Thakre, who's our Quantum Open Source Fellow, as well as alumni that have now moved to other institutions. So this is our technical staff. And all of these folks are involved in some of our open source projects, and in some cases they're themselves maintainers and creators of some tools that are used by the community. This is our board of directors, which I'm glad to be part of, together with experts coming from the world of technology, investments, software development, research-focused organizations. And all we do is thanks to the support we get as a nonprofit organization. To do so, we have an annual program to fund our ecosystem activities and sponsored research. This year, core and supporting members, it's 2 tiers, can be found in this slide. There are IBM Quantum, Scientifica Venture Capital, and Quantum Italia, Dora Hacks, Microsoft Pascal, IonQ, AWS, Sandbox AQ, and QCware. And we have many more supporters that have supported us through the years, also as part of the member program or other programs that you see listed on the right. And I would also like to mention institutional supporters, which are the funding agencies such as the US Department of Energy, the National Science Foundation, or the Wellcome Leap that fund part of the research and technology transfer that we perform in-house with collaborators at Unitary Fund. So speaking about the microgrants, they're small grants, but they have a big impact. We've awarded to date grants in more than 31 countries, 100 projects, actually exactly 31 countries, 100 projects that have led to many publications, a lot of code, so you can also find like GitHub metrics such as stars and forks. And this is everything that is a misfit for things that go from a venture fund startup and academic research that fits in papers. Everything in between is a good fit. And it's very easy to apply, and it just takes 5 minutes with a video online application. So when you look at the kind of impact, which I will spend some time on, that has been obtained with this program, it is really impressive to see that it's been funded roughly with something just of the order of what would be like 2 fully funded PhD studentships in a US university. This is like the cost for a university to fund 2 full-time students. And in some cases, I'm showing here this quote, we've seen sort of like network effects. And I will give some other examples, but one of the first grants was given to a collective of researchers in Armenia, who this project, IT42, was instrumental to start the national program in that country in quantum technologies and quantum computing. So what kind of projects we funded? So actually I'm using here 3 examples that have to do with Julia. So we would say like 4% of grants now have been given to Julia projects, which is not much. We'll get to more metrics later on. Definitely this space in software is dominated by Python at this point in quantum. One of these projects is the Marta CT, which is actually a software package for medical diagnostics that uses quantum tomography-inspired techniques for state reconstruction in order to reduce the radiation dose patients receive. Then there is Yao.jl, and specifically a part of Yao that was already established as a group and software, which was a domain-specific language compiler development. I will spend some words on this. And then we gave 2 grants. One was a follow-up grant to Piccolo.jl, which is a quantum optimal control package in Julia based on a method called Pate integrator collocation. And so talking about network effects, the Yao.jl grant was actually a project inspired by another project in Python called PyZX that actually applies ZX calculus to use its diagrammatic techniques to simplify the compilation of quantum circuits and automate them. And so the inspiration of the Yao.jl folks by PyZX led to this Yao-Lang domain-specific language, which was a part of the funded activities by Unitary Fund. And this kind of network effect is something that we see doing and we're involved in doing more and more at Unitary Fund. You see here from the Penny Link page, many integration and plugins they have. And one that has just been added this week is the Crack GPU accelerated simulator developed by Unitary Fund as a possible backend of Penny and also integrated with the Catalyst project, which is part of Penny as a just-in-time MLIR system. We also support talent working on several projects. So I'm really glad to announce that this week, the joining of Purva Thakre as part of a Unitary Fund team actually doesn't feel like welcoming Purva as a new member, because she's been collaborating with our community and our team for so long. So here you see just some examples of things and projects where Purva has helped as a volunteer contributor to Mythic over the years, helping develop benchmarks or polytwirling capabilities in this error mitigation package. Then as a Google Summer of Code student supported by NumFocus, working on the QTIP quantum information processing package to develop a technique and method to generalize unitaries and compile them in specific native gates. She's been then a Unitary Fund ambassador. She worked, funded by Unitary Fund, on a microgrant to work on Tokito, which is a project developed mainly by Vincent Russo that helps with non-local games and quantum information. And most recently, she's now a quantum open source fellow, funded thanks to funding from the National Science Foundation. As part of our community activities, I would say the center of these activities is the Unitary Fund Discord server. We have many projects that hold their community calls and office hours on them. You can see here a selection. One of them is Piccolo.jl itself. And you can also see here on the right an example of a Quantum Wednesday talk that we're hosting regularly almost every Wednesday. So you can find more at the QR code. In terms of projects that we support, one that I would like to mention because of its impact and my direct involvement is QTIP, the Quantum Toolbox in Python. So it's a great toolbox to simulate noise in general cavity QED systems. It has a collection of dynamical solvers using various techniques from Monte Carlo solvers with trajectory approaches to master equations, non-Markovian effects. And you can see here also nice usage of tools, for example, for block sphere representation of qubit evolution, as well as tomography, thanks to the Wigner function, which is also the Schrödinger cat is actually the symbol of the QTIP project itself. And myself have been involved in developing permutational symmetric modules to help characterize not just single qubits in a cavity, but a variety of qubits and spin interacting together in a dissipative way as well as coherently. So looking at emergent systems and behaviors that could happen there. So talking about QTIP and the support of Unitary Fund has given, together with being involved in other projects and programs we helped establish a governance for the project, which was started at Riken in Franco Norris group, but actually was getting help from researchers and contributors worldwide, as well as other professors. So we helped set a charter, set up an admin team with regular meetings and a board, and also give annual reports. And recently, we held the second Qt Developers Workshop at Riken in March 2024. The first one had just about 5 to 6 people. This one had around 30 people joining. And this project has over 1 million downloads, so the impact to research is really cumbersome. It's great. So how does the Quantum Toolbox in Python get entangled with Julia? Well, recently we started hosting on the QTIP organization the Quantum Toolbox.jl project developed by Alberto Mercurio Luca Gravina and Yi Te one. There are also some other quantum optics simulators in Julia. What the quantum toolbox in Julia does is exactly be as similar as possible to Qtip. So if you come from Python, you're gonna use it very similarly. Here's an example with EmiSolve, the famous master question solver in Qtip. You see the syntax is basically identical in Julia, plus you get that it's so easy to integrate, for example, with GPU and CUDA resources. And also you'll notice, I'm happy to have inspired the logo with the three cat code, Schrödinger code interference fringes in the tomography of a Wigner function inspired by Julia. So I spoke about, here we are at JuliaCon. We also started hosting our UnitaryCon events. The first one was in Rome last year. The next one will be in September at Aalto University in Finland. And it's like a great event to bring together the growing developers community in quantum technologies. Last year, the headline sponsor was Quantum Italia. So a Unitary Fund will also run a survey. You can find the results online on our blog. And this is really great resource to start tracking now also with the historical data. What are the most popular services and tools by and for the quantum software developers? So here you see, for example, the popularity of cloud service providers in quantum. And I also think it's interesting to have a look at what programming languages responders use in developing quantum software. So you see here a predominance of Python, which is pretty stable, decrease of C++, Mathematica, and clear growth of Rust and Julia. Julia currently up 14%. You can delve more into the results of the last survey, and you will also find out that Julia fares very high in terms of what languages folks would like to pick up as new programming language. And there's many filters that you can dynamically apply to see what are the replies for researchers, for students, for people working at startups or enterprises. And here again, this is like the aggregated data for all respondents. You see that Rust and Julia, about a third of folks would like to pick them up as new tools. I briefly mentioned open hardware, and here let me give a bit more details. What's open hardware in quantum technology? It's the counterpart of classical electronics such as Arduino and Raspberry Pi in quantum. We actually wrote a review reporting on the first projects that are active in this space. You can find it published in APL Quantum, the first issue. And by open hardware, we mean, as highlighted by this graph, everything that is between the device prototyping and, for example, tools such as PyAPR, or the mask design of superconducting circuits with KQ circuits based on K-layout programs, to the open access to facilities such as foundries for fabrication, to whatever software is involved, such as KIC, in sustained operation, testing and characterization of devices. So for example, the KIC project, the Quantum Instrumentation Control Kit, is both software and system on a chip with fast controls enabled by FPGAs that you can see shown here. And you can delve more about information about how these projects are scattered through different and spread through the different verticals. You can also find some projects that have to do with specific capabilities, and one of them, blockade.jl, is in Julia. It stands out, and I'm sure there's also some other projects in Julia too, such as the painter qubits devices.jl. So this is like a summary slide of the kind of activities at Unitary Fund we do supporting open quantum hardware. We also give grants to open quantum hardware projects. We support some of them in our hackathon, which I will speak about. KIC hosts its community calls weekly on our Discord, and we are partners of the Open Quantum Design program and foundation at University of centered in Waterloo. So what's Unitary Hack? It's a great program that helps supporting existing projects in quantum technology that are open source. Here you can see some screenshots about two projects that got bounties up for grabs, asking help from the community to solve them. And these bounties are nothing else than issues. If you click on them, our automated APIs will take you to the open issue that is on GitHub. It's great for maintainers, it's great for newcomers, it's great for folks who want to help out. It's the fourth year we run the program, and this year we had our largest event yet, 800 participants, over 50 projects, and actually this slide is not updated, it's more than 70 bounty hackers were involved, more than 65 for sure bounty hackers were involved, and they claimed up to 10K in bounties. This year we also had in-person meetings in Mexico, in Finland, and in the US. And this is another example of a project that got some issues solved thanks to the project itself. So this one a great thing of this program and this event. Sometimes in hackathons, the problems are not so relevant. These problems are thorny issues that maintainers would like help from the community. We also have like a gamification part of it. So there is a hackathon leaderboard, and you can see folks actually like this user Golanor supporting different projects. So this is great because they have many projects in the space. And we also have some Julia projects such as Bracket Simulator.jl, Piccolo.jl, and Bracket.jl this year participating. And this is a great way to help newcomers get into quantum. So this is an example of a developer who is an open source software freelancer who first got into quantum thanks to Unitary Hack. Actually was in the top 3 performers in terms of bounties. He then got a micro grant to develop its own project, ClassKit, a Python to quantum compiler. And this year, ClassKit got some community help by participating as a project in Unitary Hack 2024. So now, before switching to...
Yeah, we're running out of time. This will be online later. So we still have the talk still have 5 minutes. So I'll stop here. And if you have questions regarding the previous part of the talk, feel free to ask me after the session. And we'll have the next talk.
So we have 2 more lightning talks left in the session, just because some folks have come in, including if that was the speakers for those. I'm the moderator. I have a yellow card that's 5 minutes and a red card that's 1 minute left. And also for people who would like to ask questions, time permitting, just make sure I get the microphone to you before you ask a question. You guys are welcome to go sign up. And thank you, Roger. Also, one more quick shout out, Unitary Fund, who were speaking just there, also sponsored the Quantum Mini, so thanks to them for that. And if you want to know more about what they're doing, definitely come to the Quantum Mini after lunch, which will be in the same room starting 2 p.m. Okay. I'm always looking at the back of my head.
Shall we sit? Huh?
Yeah.
Better than
Yes. Yeah.
There we go. This is good.
Yeah. Okay, welcome everyone. Today we are going to talk about our Julia-based open source package. It's called Molkit from our startup Molkit for quantum simulation and also quantum computing assisted by machine learning and AI. And together, me, Taha Salim, and my co-founder, Alain Chancey, we are going to present that. Feel free to check those links for more information. A bit of ourselves. I'm co-founder of Molkit, and also I work on a part-time basis as a quantum education officer in Amsterdam University of Applied Sciences, and about to finish a PhD in computational chemistry.
So my name is Alain Chancey from France. I'm co-founder of Molkit. I am also a co-author of a book, Quantum Chemistry and Computing for the Curious, illustrated with Python and Qiskit code. I'm also a Qiskit advocate. For more details, please have a look at my LinkedIn profile. Thank you.
Okay, so here I'm highlighting quickly the features in our package. So we have two things. We have efficient quantum circuit simulator that's Julia-based. That's to help in performing chemistry simulations. So we have developed our own quantum simulator, and you can freely construct the quantum circuits and building your own quantum algorithms. These algorithms are required to be running on a quantum computer. There are several libraries are built in, so they could be used freely. And of course, that package is easy to interface with Qiskit. So in the case that you want to run it on an actual quantum hardware, that's easy to be interfaced. On the right, we see a few screenshots of the code and the kind of simulation and how it is in operating gates and so on. And the second part is the quantum molecular simulation. So that's the main purpose of the package, because we develop also a quantum dynamics simulator. We have built-in constructors for molecular Hamiltonians. Any molecular system, it has to be described as a Hamiltonian, and those Hamiltonians are quite complicated and computationally intensive. For example, rotational vibration Hamiltonian of diatomic and triatomic molecules. We need very huge matrices to solve and get the properties of these that are encoded in what we call wave functions. And we see here an example of these wave functions here, and of course the kind of matrix elements you get. But because of this complexity, we thought about making generic scheme using machine learning and AI, where you can deduce and compute those wave functions on the fly.
So this is the artificial intelligence part. Of course, we leverage the packages, surrogates.jl, which lies on top of Flux. And we very easily, in about a week, developed a proof of value that we could train a neural network surrogate function to very closely reproduce the wave functions for a number of different use cases, different states, and different values of frequency. On these screenshots, you can see different values of the states, so the different number of crests. And on the right-hand side, you can have a look at the actual code, which is actually fairly compact. And of course, this is made available on the Molkit GitHub site, and you can reproduce the experiments. So, so this is in progress. We have demonstrated on like a toy model that it works fine. And this is only the beginning. We intend to gradually demonstrate the efficiency of providing surrogate functions for these wave functions. That's it. Thank you.
And as Alain highlighted, this is a quick demo, so feel free to reach out to us for more extensive demos. That's just a quick look how we generate those with functions. We have many more libraries, but of course it's still work in progress, so we are continuously developing it. So feel free to reach us, to reach out to us, and of course you can reach us on LinkedIn. And also you can check our GitHub repo, but also website if you'd like to try it on Jupyter Hub itself. So yeah, by this, yeah, that's our presentation. So waiting for questions.
Thanks very much to the speakers. Is this on?
Oh, okay.
So do we have any questions for our presenters? Just make sure you get the microphone so that people on the stream can hear it. And yeah.
Thanks. Molecular quantum dynamics, it's an age-old problem in theoretical chemistry, right? So is your software compatible with the state-of-the-art, or competitive with the state-of-the-art of what quantum chemists have been doing?
So you, by state of the art, do you mean to include the state of the art methods, or the computational part where it's more efficient and more optimized?
Yeah, from the computation side, or I guess you're trying to solve this on a quantum computer, but of course classical computation of quantum molecular dynamics. MCTDH, for example, has been really successful there. Is what you're doing competitive on that level now, or is it going to be competitive in the future when you have quantum computers there?
So thanks for the question. That's very interesting. So regarding MCTDH is like multi-Hartree configuration methods. So what we do, we have two parts. We have the quantum computing part. So we have our own simulator to check. So we have to do certain of mapping the classical problem on a quantum computer. So this is for proof of concept use cases. And together with that, we have our classical code that we try the machine learning and AI with it. And in the future, in the pipeline, we would like to integrate both to see which part could be benefit from the quantum part and from machine learning. And the MCTDH is very good candidate because of this basis set that they have. So it's very good candidate for machine learning. Anything with kernel, that will be perfect to compute spectra and the transitions and all of that. So that's definitely indeed in our scope. So feel free, we can talk after the presentation and about this further. Yeah, thanks.
We probably have time for one more question, if anybody has anything else they'd like to ask the speakers. Also, in the meantime, for those of you standing, there's lots of seats on this side of the room.
I want to know, in terms of efficiency, is there any difference between the classical molecular dynamics and quantum molecular dynamics for example, for numerical efficiency, for parallelization, or scalability?
So thanks for the question. I would like to highlight that quantum molecular dynamics by itself is something separate from quantum computing. So it is mainly you use classical quantum dynamics with the nuclear motion, and then you combine this together and you have quantum molecular dynamics, which is sort of quantum methods to describe molecular motion and chemical interactions and the chemical reactions as well. So, but performing quantum molecular dynamics on a quantum computer, that's a separate thing. So far there is no efficiency because the quantum computing is still in its infancy, it's still work in progress. So we are working on use cases in that. But together in parallel, we're also working on a classical libraries that can use the machine learning and AI in optimizing those things, and until we find the sweet spot where they could be merged together.
So I think that probably takes us to time. So thanks again to the speakers and the questions.
That's fine. All right, hi everyone. I'm Greg Piers. I'm a research scientist at the AWS Center for Quantum Computing. Today I'm talking about the computer-aided design of quantum integrated circuits, or how we're using Julia to design quantum hardware. So some background. The devices we're designing are integrated circuits in that they're fabricated like most any computer chip, layer by layer in different materials, different microscopic patterns, on top of a single substrate like a silicon chip. They're quantum in that we want to take advantage of quantum physics, like superposition and interference, to do computation. The approach that we're taking is one among many. We use what are called superconducting qubits, or quantum bits, where the quantum part comes from the physics of superconductors. So here's a picture of one of our chips, the gray square in the middle. It's inside of a larger package. The whole thing fits in the palm of my hand. We would then close this up, put it in a refrigerator where we operate the device at a fraction of a degree above absolute zero. So that's all to say that the problems we're thinking about, some of them are inherited from traditional electronics, and many of them are specific to the design of a quantum device. So that's a quantum integrated circuit. The other half of my title, computer-aided design, can encompass a few things in our case. One is geometry. So this is a representation of the device as 2D shapes with information about the material layers they correspond to. So in this graphic here, we have black, where we want to remove some metal from the first layer, and red, where we're depositing some other material to get basically a wire with some bridges over it, sort of a toy example. But that's the sort of thing we would send off to be fabricated to get a real device. We also work with higher level descriptions of devices. So the schematic, which I'll say more about later, describes what are the components in the device, how are they connected. And then there's a lot of physical modeling that goes into a design. The part that I'll focus on is finite element simulations of electromagnetism. That's closely tied to both of these other two things. And I'll get into that more later. So the design cycle goes back and forth iteratively between all of these things. And ideally, you want a single tool that ties them all together. And so we've internally developed a package we've been calling layout.jl to do that. It's now mature enough we're having discussions about open sourcing it, not necessarily under that name, hence the quotes, but if you're interested in any potential future release, please get in touch. Pending that, I'm going to focus on the problems we're solving and how we're using Julia rather than showing code. So this started out as an internal fork of a package called devices.jl from an academic group with close ties to us, a lot of the same people. But we found that if we wanted to scale up to devices that are larger than academic demonstrations with a few qubits, we identified some things that would be bottlenecks going forward. So one of these was the layout workflow itself. Designers don't want to be working directly with geometry all the time, which polygon goes where. They want to work in terms of how components are parameterized and how they're connected. So that's called schematic-driven layout. We added a nice interface for that. Another focus area has been the simulation pipeline. We want to automate as much as possible. So to that end, we developed a bunch of new geometry features, including 3D modeling to produce meshes and configurations that we can then use to call out to external simulation tools. And finally, less technical, but still very important, has been designer collaboration. As our team grows and we're building more on our own past work, we've built tooling to leverage the Julia package manager as much as possible. So a device design is a Julia project, fully reproducible. We manage a library of components in a private registry, our process development kit, or PDK. And with that, I'll zoom in on a couple of these things, starting with the schematic-driven layout. This is the idea that a designer works with some kind of abstract representation, like on the left, to produce an actual device, like on the right. So in more detail, this is a PowerPoint illustration. The designer is working in code, but they're building a graph with metadata where the nodes are the different kinds of components. So say in yellow, those dots are 3 qubits on this device, and then the edges are connections between them. So this port of this qubit is connected to that port of that qubit. And it turns out that's enough information, if we're pulling all of these different components from our library, to then automatically generate the layout for the device on the right. So we're doing placement and routing based on the schematic. And so on the right, we have a microscope image of an actual device in false color to show the different kinds of components. And there's a paper, the QR code, for what we did with that. Then for the simulation pipeline, this is talking about going from a 2D representation of our device together with information about the fabrication process to generate a 3D model. We use the Open Cascade geometry kernel via the gmesh.jl interface package, and then generate a 3D mesh, which we then use for finite element simulation. The tool we use for that, we've also developed in our team. It's called Palace, which we use for large-scale electromagnetic simulations over hundreds or thousands of cores. It's not in Julia, but it's very cool. You should check it out. And what I want to zoom in on here is the meshing. So mesh in the finite element method is a discretization of space that allows us to turn Maxwell's equations for electromagnetism into a numerical linear algebra problem. And the quality of the mesh strongly affects how well behaved that problem is. As you throw more resources at it, its accuracy, its convergence. So if you do sort of the naive thing, if you're working with a polygon-centric tool, which is very reasonable, a lot of in the end fabrication tools are going to want polygons to draw the device. If you have a nice curved wire here, these are circular arcs, but we've discretized them too early. They're now piecewise linear shapes with a ton of points on them, and the mesh wants to connect all of those points, and we end up with a lot of long, skinny triangles, which is bad. But that's not a constraint of the 3D geometry kernel or the mesh itself. You can have even curved mesh elements. So if we sort of hang on to this exact geometry information as long as possible, as well as things like the physical information about what layers we have and even design intent, we can use all of that information to make the best mesh that we can. So hopefully that already gives an idea of why we think Julia is such a good fit for this problem. It allows us to have these rich geometry abstractions with low overhead that we just carry through until we dispatch on whatever backend we want to render to, whether it's a geometry backend or this 3D simulation inputs. And of course, reasons everyone likes Julia, good performance, fast onboarding for scientists, even without a whole lot of Julia experience. As I mentioned, it's great for reproducibility and collaboration. The package manager is best in class. We leverage the ecosystem as much as possible. I'm not going to read all of these off, but I'll just finish. Thank you for everyone who's contributed to the ecosystem. Thank you to my team for making this possible, and thank you all for your time.
So we're at time. If you would like to ask the speaker a question, we have a 10-minute break, so I guess we can pass the microphone over. Or if you'd like to go to the break before the keynote, feel free to do so. Our next keynote is Andrew Fitzgibbon, who just got elected a Fellow of the Royal Society. But you have a question?
Does it output like a GDS file?
Yeah, that's the main format that we support. There are other 2D graphical formats with sort of bare bones support, like DXF, SVG, but mainly GDS.
It's open source?
Not as of this moment.
But you're planning to open source the main package?
I can't say for sure, but we're discussing it. Yep.
Okay, thank you.
Thanks. we have one more question.
How do you define a good mesh to match the certain accuracy, especially in electromagnetic problem?
Yeah, so it's something that you have to test at first. So you can either benchmark against problems with known solutions or do refinement studies where you take a starting mesh and decrease the element size and see how the solution you get behaves as you do that. And then with experience, you learn which sorts of meshes are good for which sorts of geometries.
All right, so we should definitely head to the break now. We'll have the Quantum Mini Symposium in this room after lunch at 2 p.m., so definitely come back for that. Thank you again to all of our speakers and also to Unitary Fund for funding the Quantum Mini later. Enjoy the snack and the keynote. See you back here at 2. And thank you also to our
to the quantum meeting. We have so now this is a tradition. We have a quantum meeting symposium every year, well, as you can see, our community is growing larger and larger. We have a specialized sponsor this year, thanks to Unitary Fund. And we have the first speaker from my collaborator's Jingguo's group, Zhong Yini. This is a very interesting work that happens inside the Julia community almost randomly. You will learn how this happened, I guess, in Zhong Yi's talk. I'll let Zhong Yi give the talk. Thank you.
Okay. Thanks for the introducing, and thanks for you to come to my talk. I'm Zhong Yini, a PhD student from the Hong Kong University of Science and Technology, Guangzhou. Today I'm going to introduce my Julia package, TensorQEC, which is a quantum error correction package based on tensor networks. This work is done with my advisor, Professor Jingguo Liu. Okay. For today's talk, I'm going to introduce the basic ideas of the quantum error correction first, and then I'll show how we infer the Pauli errors with tensor networks, and after that, I will introduce how we use tensor networks to simulate coherent errors. There is already a Julia quantum error correction package called Quantum Clifford, which includes Clifford circuits, graph states, and other quantum stabilizer formalism tools. So why do we need TensorQEC? The main reason is that their simulation of Clifford circuits is mainly based on the Tableau's method, which doesn't work for a non-Clifford circuit. And also, we use tensor networks to inference errors, and our package is very compatible with YAO. Okay. So what is a quantum error correction? A quantum error correction code is usually defined by a set of Pauli strings called stabilizers. For example, here we have S1, S2, and S minus K are stabilizers. Inside this circle is a eigenstates to S1 with eigenvalue 1, and inside this circle are eigenstates to S2 with eigenvalue 1, and so on. The intersection of these circles is a coding space. We encode our quantum state from a larger Hilbert space into this coding space, and we measure the stabilizers frequently to check that. If the measurement outcome are all 1, then we know this quantum state is surely inside this coding space. If not, we can infer the error with measurement outcomes and correct it. Okay. The whole quantum error correction procedure is shown here. We first encode our data qubit with some ancilla qubits into the logical state, and then some error may happen. Then we extract the syndrome into some other ancilla qubits and measure them. Based on the measurement outcome, we can infer where and what type of error it is actually happened, and by applying the inverse of this error, we can correct it. We may repeat this measurement and correction procedure for several times during the whole quantum computation process. Finally, we can decode the logical state and measure them to get the computation outcomes. Okay, here we take STIN code as an example. We use 7 data qubits, those white dots, encode 1 logical qubit. We have 6 stabilizers, x1, 3, 5, 7, x2, 3, 6, 7, x4, 5, 6, 7, and also z-type z1, 3, 5, 7, and so on. In tensor QEC, we can define a string code instance with this string code and get stabilizers of it by stabilizers. Here we can see we get x1, 3, 5, 7, x2, 3, 6, 7, and so on. This function here encodes stabilizers, takes the stabilizers and outputs the encoding circuit for this string code. We can visualize this circuit by this circuit in YAO. This data position records where the data qubits we put, and the rest qubits are initialized in the 0 state. And this bimatrix here records more encoding information, and we may use it later. Also, we can generate a measurement circuit with this function. It takes the stabilizers. Stabilizers 4 to 6 are these stabilizers. Here we only generate the measurement circuit for these stabilizers. Here we get the measurement circuit and the position where the stabilizers are measured to, 15 to 17. We can visualize this circuit. The first 7 qubits are data qubits, and we just encode our data in. And then we first copy the error into some ancilla qubits and measure the stabilizers on it. This qubits 15 measures the stabilizer Z1, 3, 5, 7, and this qubit 16 measures the stabilizer 2, 3, 6, 7, and the last one. Okay, let's see what will happen if there's a poly error happen in this circuit. For example, we have an X error happen on the 6th qubit. To see how this error propagating through this quantum circuit, we first define this error as a polystring. There's 17 qubits in total. The 6th position is this X, and this Clifford simulates function show us how this simulate how this polystring propagating through this measurement circuit. The rest output is the final polystring. Also, this structure rest records all the history of this propagating, so we can generate the history in this figures folder, and we draw a GIF with those pictures. As you can see, this X here is propagating through this circuit. Okay, and okay. First, we copy this error from here to here, and then we measure the stabilizers. Since poly X and poly Z are anti-commute to each other, so the Z stabilizers contains this error qubit 6 will be flipped, and the rest stabilizers will stay the same. The first stabilizer, Z 1, 3, 5, 7, stays the same, and the other 2, 3, 6, 7, and 4, 5, 6, 7 contain 6. So they are flipped. After this circuit, we measure the last 3 qubits to get the syndrome of the stabilizers. We will get a syndrome 1, -1, -1 here, and then we know there's an error happened on the 6th qubit. Take another example. If the measurement outcome is 1, 1, -1, then we will know the qubit 1, 3, 5, 7 and the 2, 3, 6, 7 are there's no error on them, so the error is on the qubit 4. Okay, generally this is an inference problem. We have the measurement outcome of some of the stabilizers, and we also have a prior error rate on the physical qubits. We need to infer what error is actually happen on the physical qubits. The most intuitive way for this problem is to make a truth table. Here we can make a truth table with make table, and it takes the stabilizers. And the 1 here means this table only contains single qubit errors. Since string code is only capable of correcting single qubit error. Again, you can see if the last two stabilizers are errored, the Z2, 3, 6, 7, Z4, 5, 6, 7 are errored, then we know there's an XLU error happened. Okay. However, to make a truth table for large code, the truth table may be significantly large, and also it doesn't contain any prior error rate in it. So here I will introduce how we use tensor network to inference the error. First, this inference problem is actually an MMAP problem, which means that we have some evidence on some variables. We have some variables to be marginalized, and we the distribution on the rest of variables we actually want to infer. The evidence is the measurement outcome of the stabilizers. The variables to be marginalized is the intermediate state during the in the circuit, and distribution we want to infer is error distribution on the physical qubits. Okay, and to solve this MMAP problem, we first transfer this quantum circuit into a tensor network and use this Julia package tensor inference.jl to solve this probabilistic problem. Okay. Okay. Now we use YAO to simulate a real physical device and perform quantum error correction procedure on it, and use our package to infer what error is actually happened. First, we generate a random single qubit state data and place it on the data position. The other qubits are initialized in 0 state. That's our initial state. Then we apply the encoding circuit here to encode this initial state to the logical state. Then we manually apply an X6 on the 6th qubit to simulate there's an poly X error happened on the 6th qubit. Then we can measure the stabilizers on the logical state. The stabilizers, the first 4 stabilizers, first 3 are X stabilizers, and the fourth is Z1357 stays the same, and the last 2 stabilizers are flipped. That's a measurement outcome. Also, we need to define the prior probability for each physical qubit. Here, we mean there's 85% of probability that this physical qubit stays, there's no error on it, and 5% of probability that there's an X or Y or V error on it, respectively. Okay, we put our measurement outcome, the bimatrix, the encoding circuit, and this, the prior probability into this function inference. We get the error polystring, which is exactly the X6 we applied on it. By applying the inverse of it, we can correct this error, and then we measure the stabilizers. It will become all 1 now. Also, we can decode this logical state and check the fidelity between it and the original one. Okay. Besides random poly error, there's another type of error called coherent error. A random poly error is that there's a classical possibility that the qubit is flipped or not, which is usually caused by the environment noise of the physical device. For coherent error, it is usually caused by inaccurate operations. For example, we use maybe laser beams to apply an X gate on a single qubit, which is a rotation around the x-axis, right? And maybe the laser is not long enough or the amplitude is not correct. The rotation angle or the rotation axis may be slightly different from the ideal one. So the outcome may be not exactly this direction. That's a coherent error. For random Pauli error, we have Clifford circuit simulation to simulate it effectively. And there's a threshold theorem told us that if the error rate is below a certain value, we can use a large enough code to correct it. However, coherent error gates are no longer Clifford gates, making it difficult to simulate. And also, we don't know whether the threshold theorem holds for this coherent error. Here, I will introduce how we use tensor networks to simulate a coherent error quantum circuit. Actually, any quantum circuit can be simulated with tensor networks. Since quantum states are vectors and unitaries are matrices, they are all tensors, right? And we can connect a quantum state and a unitary to get the final state psi prime. And also for density matrix, it works like the same. Okay. We believe that in some situations, tensor network is an efficient representation of quantum states and an efficient simulation of quantum dynamics. However, for highly entangled states or deep circuits, there may be no advantage. Okay. In our package, we first define the stabilizers and the encoding circuits as before. And we construct a circuit with YAO. Here we first encode the initial state into the logical state, and then we apply a logical X gate, which consists of 7 X gates on all qubits. Then we decode the state with the encoding circuit. Now the data qubit is applied an X gate on it, so we apply this X gate back to recover the initial state. This circuit is not an identity circuit to all qubits, but it should act trivially on the data qubit. To check this, we need to partial trace the amphilia qubits out, which is simply done by connect the subsystem the indices of the subsystem that we want to partial trace out together. So the tensor network representation of the previous circuit acts on the density matrix of the data qubits look like this. We initialize the amphilia qubits in 0 state and partial trace them out after the circuit. And if we contract this tensor network, we got tensor looks like this. Okay, in our package, we can transfer a quantum circuit into a tensor network with this function simulation tensor network. Also, we need to specify which qubits are data qubits and which qubits are ancilla qubits that we want to trace them out. Okay, the input indices are 6 and 13. The output indices are 50 and 86. Okay. Then we use one-more sum to optimize the contraction order of this tensor network, and then we contract it. As you can see, it is surely an identity tensor because only 1, 1, 1, 1, 2, 1, 2, 1, 1, 2, 1, 2, and 2, 2, 2, 2 elements of this tensor is 1, and the rest elements are all 0. Right. Also, we can connect the indices of this quantum channel to compute the fidelity between this quantum channel and identity channel. We can use this function to get a tensor network. Looks like that, and optimize the contraction order, and finally contract it. We can compute the infidelity of it, which is very close to 0. Okay. Now we add some coherent error in it. This function add coherent error to each quantum gate in the quantum circuit. For example, the first quantum gate in the circuit is a Hadamard gate. And after add some coherent error in it, it looks like slightly different from the original one. Also, there's a face. Okay. Still, we can transfer this errored quantum circuit into a tensor network and optimize the contraction order and compute the infidelity, which is much larger than the previous one, because there's some coherent error in the circuit, right? Okay. Too fast. For summary, we first infer the polyarrow with tensor networks, and we also use tensor network to simulate coherent errors. And our package also include other basic QEC tools like the construction of stabilizers, the construction of encoding circuit and the measurement circuit, and the simulation of Clifford circuits. Again, thanks to my advisor, Professor Jingguo Liu. Thanks for listening. Oh, okay. Do we do microphones?
Yeah, please use the mic, so that way the stream picks it up.
Thank you for the talk. This is a really interesting tool that I'm pretty sure I'll be using soon. I have a couple of questions. First, maybe more on the technical side. What are the backends for simulating this? Like, do you have your own tensor network simulator? Do you use iTensor? Same for the Clifford simulators? Sorry?
One more answer. Is another Julia package. One more answer.
That's an independent package. Or is it part of your distribution?
Oh, it's an independent package.
Thank you.
Yeah, I agree. This was very interesting. I'm kind of curious just maybe about some of these coherent error simulations and how you might play with some of your inference tools in conjunction with those types of simulations. Do these things talk to each other in a reasonable way? Could I explore basically projection of these error sources onto the kind of like standard poly air channel models or things like this using your tools?
Actually, we definitely can use this inference tools to inference a coherent error. There still may need some work.
If it's okay, can I then to follow on, and I assume it's also relatively straightforward, maybe in the current interface, if I wanted to like specify my own CU added error, a coherent error that was like unique for the whole circuit, but could I like specify individual gates having specific error models or something like this?
Oh yes, we have other interfaces like if we want to replace every X gate with the same coherent error X gate. Like this.
Okay, and then yeah, that's interesting then. Yeah. Okay.
Thank you.
Thanks. I agree. A really nice talk. Is this package mainly for, so to speak, one-dimensional architecture, or also for like a two-dimensional system when you have, like, could you build, I don't know, an IBM architecture or something similar with it?
Qubit, you mean?
Yes, just anything like a two-dimensional system where you have like many connections between different qubits and gates on top of that.
It's mainly based on the stabilizer formalism, which I believe is only works for qubits now.
Thanks. Thanks again. We're running out of time, and maybe we'll have the next talk. Is it Aaron? About pickle. Am I pronouncing correctly? Yeah, if you have more questions, please feel free to reach out to Yui later. Also, announcement that we will have a quantum dinner tonight, and if you want to come dinner with your colleagues in quantum community, come back here or meet up here after all the talks is done, around 6. So,
cool. Is it flashing a lot? That's not ideal.
I figure if I just shuffle it around on the table, it'll be better.
Let's try another plug.
Like other stuff in your presentation or in what you want to present.
Yeah, we're just while this is we're futzing with this. I'm
Do you have a different adapter?
I do not. Let's try this. Oh, okay. Let's see. Is this gonna? Okay. All right. No. We're gonna switch this up. There is. Okay. Sweet.
Be attached.
Right in time. We're still we're a little early on time too, even. Beautiful.
Well, if you can get this on the screen.
One would hope.
Well, we can. I mean, it's Google Slides. We could pull.
What? You got two there? Let's. Let me try this other side of this.
Oh, yeah.
And maybe it's the adapter. Yeah, I'll try one of your. Oh wait, there we are. Let's see if we have the flashing green. No, all right, we're in business. Beautiful. I appreciate the double. You came way more prepared than I did, but I'm appreciative that there are so many available. Yeah, so I'm Aaron Trowbridge. I'm at Carnegie Mellon University in a robotics lab, actually, where we work on control algorithms. This is Andy Goldschmidt. He is a postdoc at UChicago, who also works in this kind of robotics-y flavored control for quantum computers. So we do pulse design. We design like the pulses that actually run and control the qubits at the lowest level. Hence, like our logo this year. If you were at JuliaCon last summer in Boston, we did not have this yet. So this was a new design that I thought was clever. I should mention, so Piccolo.jl is a meta package that includes 3 sub-packages. So I recommend, if you're going to check out the documentation, quantum collocation.jl is kind of where the main documentation lives. Name trajectories handles like trajectory data, and then trajectory indexing utils is small but pretty self-explanatory. So like, why do quantum control and why build a software package to do it? So there are a lot of interesting problems in this area. So like in neutral atoms, you might have different design requirements. You might want to build a time optimal gate that kind of rails your control on and off. Or you might want some smoothly changing pulse to control some sort of atom interactions with your lasers. Cat qubits require interesting control designs because they live in coherent state space, and then also like some recent work on optimal control for readout of these qubits was very interesting. We actually have like tested a lot on transmon systems. So we worked with the Schuster lab that was at UChicago, is now at Stanford. So this QR code will take you to a link kind of demoing some of the transmon tools we've built, which like leakage is a problem. So we heard in the last talk about the qubit space for doing quantum error correction. If you leak into higher levels of your qubits, you actually will not be able to account for those errors anymore. So staying in the qubit space is very important. So like, how do we vision people using this package? Usually you start off with a Hamiltonian description of your system, and you'll construct in our language a quantum system that will basically handle that drift and drive Hamiltonians. You'll also define a goal state, and you can do this in a couple different ways, where you could just say, I want a goal unitary, or you can even do some sort of embedded unitary in a higher level space. You can embed a subspace unitary, so you might want to do this for some of these when you're modeling higher levels that you don't want to leak into, but you want to do a qubit gate. And then you'll build a quantum control problem. So if you guys, anyone will look into this, last year we gave a talk on like what this package actually does underlying. So this is borrowing from robotics direct optimization and solving direct collocation, hence the piccolo in the name. But basically you're solving an optimization problem over the states themselves, so the wave function, the unitary, the controls, and the time steps. And you have some objective over this. It could be your fidelity objective, objectives on the controls, whatever. And then also, interestingly, in this case, an integrator that links states at one time to states at a previous time. So this is like a nonlinear constraint that actually enforces your dynamics. So you can actually parallelize over all the time steps in a solver. And like put one of these constraints on each core, and you can get a lot of interesting advantages out of solving quantum collocation problems in this way, as opposed to like a shooting great method. And then also you can put constraints on the states themselves. You can put constraints on the controls, time steps, do whatever. You can do very interesting things with constraints. So how this looks in the interface, basically like we have a certain type of problem called a unitary smooth pulse problem. And this handles like designing pulses that have a certain controllable level of smoothness to them by actually bounding the second derivative of the control. So you can pass an abstract quantum system, you can pass your goal state and quantum operator, you tell it how many time steps you want and what should be the size of that time step. And then there's a lot of options for the underlying IP op solver and also the Piccolo options themselves. So we have a lot of different problem templates that we have set up for users to use based on different problem settings. So smooth pulse problems, bang bang problems, which you want to like basically turn the controls off and turn them off, turn them on and turn them off. Robustness problems, you want to be robust to certain types of errors. Minimum time problems, where you constrain the final fidelity to be a certain value and then solve for the shortest gate you can do, which you can't really do in an indirect method. And you can do it here, which is very cool. And we'll see that later. Sampling problems, direct sum problems. You can do stuff for quantum states as well, pretty much all the same things. And we're also right now working on density matrix control problems. So this is like kind of the main philosophy is like there's a lot of different problem settings that you might want to solve, either minimum time or robustness or joint problems or any of this. You want smooth pulses. So you can do all of that in this framework. You can also, like, very interestingly with the name trajectories, you can kind of like concatenate them together in a direct sum problem and then solve sampling-based robustness problems in this way. It's very cool. And we'll see some of that, I think. Okay, so from last year, we have gone from 0.1 to 0.3. We've added a bunch of new features, including quantum system templates, which lets you create quantum systems in a parameterized way and recreate them with new parameters. Embedded operators for handling the subspace stuff, leakage suppression, utilities for like looking at your Lie algebra space and deciding, like, basically determining if your problem is controllable, so you can actually reach the goal state you want to get to, which is very cool. Theory, and then also a lot of underlying infrastructure for the packages in this package ecosystems, including using testitems.jl to handle a lot of our tests, which we've been focusing on. At this point, I'm going to hand it over to Andy to do a code demo. So if we go this way, we can go right here.
Okay, yeah. Okay, well, in that case, we'll move relatively quick. I have 5 minutes. I'm not gonna run a lot of cells. Anyhow, so we're gonna start with a really simple system. It's kind of the standard test bed. Yeah, okay, we have way more time. All right, we're like 5 minutes, and we're like, all right, we'll get 20 minutes of material done. I was like, just be ready, we'll get there. Okay, we're gonna take a breather then and do this at a reasonable rate. Okay, so like Aaron described, what we're gonna walk through here is just the kind of core underlying, if you remember in the last talk, like the qubit rotations. So what we have is quantum dynamics, which we're gonna just think of, we've got a linear differential equation, or yeah, we can, yeah, you want to dial up your,
Control plus usually works.
yeah, it'll increase all the bars, so we're going to actually just increase the editor font size so that way we don't.
Is this better?
Yeah, perfect. Nice. Okay, yeah, this way these stay tiny. Okay. So if you can see, we have a system which is bilinear in states and controls. And so what we mean is like you've got your controls, they're attached to Hamiltonian operators. So those of you familiar with kind of standard linear control theory, that's kind of the subtle difference here. But we can think of these as basically acting as rotations. So you might think of basically doing some sort of kind of control for quadcopters or things like this will also use these types of methods. And so these rotations we can encode in our framework via quantum system object. So you have, for our case, we're going to just add some drift just to make it interesting. And then we're going to have two controls, so a drift operator and then our list of controls. And we're going to target this goal, which is an X gate here. And then we're just going to take a peek at our quantum system object. So we have some drift operators and then the isomorphisms and some other information in this constructor object here, which we'll talk about. And then some of our Lie algebra utilities that we've kind of been describing. This one's going to be really easy. So we made it verbose so we can just see that the Lie tree is of size 1 because, well, all these matrices are the basis for your system. But we'll look later at some other more interesting systems and how you might use that tool. Okay, so then we've got a system. Let's construct a control problem. We're going to take a certain number of time steps here and a delta t, system, goal, plug those in, and then we're just going to enforce basically the fact that we have Hessians or not Hessians depending on the kinds of things you want to do. So we're just going to make that very explicit in our options. You see we're adding a ton of constraints, doing a bunch of kind of stuff under the hood to set all this up for you. And now all you have to do is hand this off to a solver. We're going to cap, this is an IP opt option, but we give you a quick way to access the super easy ones you want. We're going to cap this at 50 iterations, run this, and check in on our fidelity. So we got a bunch of 9s. We have some plot utilities that will let you kind of inspect this trajectory object, which is one of the packages. This is a named trajectory. And we see, okay, we've got some population behavior. We basically are doing an X gate, which is a swap. You're just switching the 0 to the 1 by doing a pi rotation of that block sphere embedding that sphere. You're just swinging it around on the x-axis. And so, okay, we got an X gate, but look at all these braided wiggles, okay? So this is kind of an imprint of the initial control initialization. So you see you've got a lot of kind of arbitrary action here. This might be jostling and kind of bouncing around more than you really need to as you kind of whip around on this rotation. So what can we do? We can mess with things like, let's try a min-time problem. So we can specify a final fidelity. This can be turned off and just use the default problem fidelity. And we're just going to take in that previous problem and reconstruct a new one. And I'm going to add some stuff here basically to just turn off a lot of the printing so we don't have to deal with that. So we'll construct this problem. And then we're going to solve basically minimizing the time subject to the constraint that we keep at least 4 9s. And let's check in on things after 50 iterations. And we see, okay, some of the braiding gone. And if we look here, our total time is 6. Previously, we were more than double that. And if we let this run even longer, we'd get something more interesting, but let's kind of keep trucking along. Perfect. Okay, so yeah. I just want to jump in to the next section and say, okay, we had these smooth pulse problems. That's great. That's one category, but control hardware differs, needs differ for users, and one other setting that you might want to pursue. Bang-bang control, which is sort of the time optimal behavior for these types of bilinear control problems where you just kind of hard rotate on one axis and then you switch and you hard rotate on another axis and things like this.
And so let's give that a try. And we'll talk about how this is implemented after we see it work. So I ran this for 50 iterations. What I want to highlight is like the solver is really nice for being able to kind of just rerun things and kind of reinitialize. So let's say you didn't get what you wanted with that 50 iterations, so you want to just kind of pick back up where you left off. So we'll just do that, and okay, like now we've caught up to where we wanted to be. We'll go back to our plot utility and check in on what we've got. Okay, so now we've got a lot of the braiding. It's gone, great. And in fact, you can kind of see like that bang bang behavior. It's on, chilling here, and then off. And in fact, this little drag kind of correction, this is basically just dealing with that fact that we had that drift present on the system. So actually, if you remember in the theory slides, there was that like transmon picture, and there was that like nice Gaussian pulse, and then there was that little subtle correction. That's kind of exactly what we're seeing here. It's just dealing with the fact that there's that Z rotation, and you're just kind of like offsetting that and getting rid of that extra bit of the dynamics because you don't want that impacting your system. So how do we do this? Well, we're flexible in how we design this named trajectories object containing all of the data we're optimizing over. We're doing direct collocation. So states and controls are in this optimization problem. And so that means that like for smooth pulses, we can just directly control with the accelerations. For these kinds of problems, we can directly control with velocity, and we can penalize something like the L1 norm of the velocity and introduce sparsity. So just like a lot of standard tricks coming from control and just making sure they're accessible to the quantum community, getting all the math kind of in the right quantum dynamics settings. So, okay. So those are small, that's the standard qubit things. Let's try to like stay in the qubit space, but just stretch what we can do with that. So I'm gonna take a system here and I'm gonna make it sampleable. So I'm just gonna define a function. And I wanna just remind everyone about our previous fidelity. Looks pretty good. But let's say we apply that on a system that is not at the value that we had this drift here. And the fidelity drops. And you can see it'll like, you know, it'll get worse as we go. So, oh, right, Aaron's weird keyboard. So I'm not going to play with that. Okay, so what I'm going to do here is I've just assembled 5 systems, and I am going to coordinate them in one large problem where all the states are separate, but the controls are now shared. So they have to use the same controls, implement the same gate that they're all targeting, and do it for this sweep of systems. Okay, so the nice thing here, linear problem scaling, because we're just dealing with a bunch of qubits instead of 1 qubit. So not really a big demand on compute to get something more interesting. And what we're going to do is we're just going to take those fidelities, and we're just going to roll them out on a whole bunch of those Z values, those errors that we might have been experiencing that we want to be robust to. And so if we look, what you see here is this is the previous solution, which is dialed in at that drift that we had used in the model. But you see the robust solution kind of like bounces around at a few points that we've like included in the samples. And so we now have something which is valid. We're like below 4 or 5 nines here for like a much wider range of solutions as opposed to being like dialed into a very specific model. So this kind of model robustness is pretty critical to a lot of the design because a lot of quantum control ends up having to be open loop. Because feedback is, I mean, you just saw that whole talk on error correction. It's a challenging game. We can also sample on the goal. And so what we're going to do here is we're just going to take a rotation of this unitary about this Hamiltonian here. And we're just going to let theta vary for some amount of values. So I'm going to just construct a bunch of smooth pulse problems. And I'm going to do that in a loop for 10 thetas from 0 to pi. And then I'm going to use a direct sum problem to basically glue them together via a regularization on this A value. And I'm going to solve this and then check in on the fidelity of just one of those goals just to see what's going on. So I'm going to take the first control. I just augment these symbols here. And we're not going to have time to talk about how named trajectories works, but it's basically just a container with a bunch of symbols associated with the various parts of the state. So like a classic kind of like named array or something like this, but with some extra help for quantum systems. And so what we're doing here is we're solving now 10 qubit problems together. And so we'll see, we're going to burn a little bit more as we stream and compute at the same time. And so we'll let this run. But like at a high level, basically you can specify
anything here, and the behavior is going to kind of vary. And you see we put the fidelity constraint, so it kind of pushed right up against that boundary. And we're just trying to keep the controls together. So you see we have these plot utilities that let us kind of specify, in this case, all of the symbols, all the various controls that we are interested in. So these are all for the various angles. And you see that what we've done is we've glued them together. So now instead of having a bunch of separate rotations to different gates, we've kind of got a sweep, right? Which is telling you, okay, I know there's this kind of manifold, perhaps, in control space that's implementing this rotation. So now you have something more interpolatable to realize kind of this family of quantum gates. So that's another feature. And you know, we probably could have turned those off more efficiently. But yeah, so that's one thing you can do. And then this is just to Aaron's point. I wanna just kind of introduce these constructors for quantum systems, which is a whole separate kind of template framework, which we have some access to, and it's a little more relevant when you start to build more complicated systems. So here we're just going to take a transmon, and we're going to have our parameter just be the number of levels. So you see that you build a system just like before, drift, drives, and you construct it now with a constructor, which is just a reference to the function itself. And so when we do that, we can build a system, and then we can re-specify that parameter, or like partially specify some of the parameters, update different ones, rebuild the system. Now we have a 3-level system and a 2-level system for this transmon. And so what can we do with that? Well, let's just go back to the reachability questions and say, like, I want to implement this 2-qubit gate, which is basically identity except for in the 1-1 case in which you want to pick up a relative phase. So that's the CZ. We'll check it on a 3-level system, and we'll see, okay, we needed to go up to the 3rd level of the Lie tree. We didn't actually control in the full space, so we couldn't access all unitaries, but the gate was accessible. And we can even peek just to see, like, okay, what's going on here? This is an embedded operator, so it's zeros except for in the subspace. And we can like unembed that operator and just kind of check, okay, that's what the CZ is, so this relative phase is what you want. And if it's not the 1-1 state, so 0-1, 1-0, or 0-0-0, 1-1-0, whatever, you don't have that relative phase. Okay, so what happens if you go back to the 2-level system? Well, in this case, you actually are reliant on that drift to get the relative phase. That anharmonicity is critical for this gate. So you see that if you try to do this in a 2-level system, you terminate in some subspace, and you weren't actually able to achieve it in that subspace. And so just an example of kind of like how these reachability tools kind of speed up your design and iteration as you work through this process. So that is kind of the tutorial we have for this talk. But like I said, we had the QR code. There's another tutorial that walks through like more explicitly like transmon setting, leakage suppression, some of like the very practical stuff we did for like Schuster Lab and things like this. But I think now, just to kind of wrap up, we'll kick it back to the talk on what Piccolo looks like over the next year.
Okay, so what's next for us? We are shooting for a 1.0 version of Piccolo.jl sometime this year, so which is very exciting. So this is basically our game plan for getting to that point. Like in the moment, we're actually working on like open quantum systems. So we have a couple systems in mind that we want to test this on, specifically cat qubits, where you need to worry about the openness of the system. Also, like we listened to Chris Rakoukis' talk yesterday, and we're very inspired to get up on our docs and CI contribution and style guides. So we are very motivated to do that. We've been thinking about this, and then seeing his talk was very inspiring. We also want to integrate some of our higher level like utilities for like creating quantum operators and like Hamiltonians and stuff. We want to integrate with Quantum Toolbox to handle a lot of this, and also utilize a bunch of their tools. So Quantum Toolbox is like the Qtip version of, or it's like the Julia version of Qtip, which is starting to come online, which is exciting, through the Unitary Fund as well. Which I should have mentioned that we are a Unitary Fund sponsored project, which I didn't include the logo on the slide, sadly. I should have. So Quantum Collocation Core, we want to spin out, like basically, we have an underlying core package that deals with a lot of the solver specific stuff. We want to kind of separate that out from the higher level interface and land at a Piccolo.jl 1.0 by the end of this year. So just to highlight a few things, so it's great to be in Eindhoven Dankjewel. Also, so if you go to this QR code, this takes us to the GitHub page. We are also like kind of exploring the commercial applications of what we're working on. So we have like our company's kind of called Kestrel, and we're going to be doing the National I-Core, NSF National I-Core program this fall. We are like, I'm in the robotics exploration lab at CMU. Andy's in the EPIC group at U Chicago. We also work with the Schuster Lab very closely. We have a growing user base of people at Stanford, U Chicago, Harvard, Inflection, IBM. We're adding lots of new features, and like we're looking to get feedback and support and see if people want to contribute. So thanks to the Unitary Fund again. I can't believe I missed this thing, and that's it.
Thank you. So how about non-unitary dynamics, Lindbladians, losses? Is that covered?
Yeah. So okay. So we are working on that like at the moment. So we're heading in that direction. That's like one of our next things we're gonna do. So stay tuned. Yeah. And you'll see some stuff on GitHub probably this week maybe. And if you have any systems in mind that you would like to try this on, like please reach out, and we'd be very happy to try it out and walk you through stuff.
Yeah, that's been like honestly like one of the biggest ways to kind of build out features is getting kind of the right problems, and also because of the problem template infrastructure, we're kind of fleshing out like getting the kind of core. Okay, this kind of template matters to this community. Like that's how we've kind of tapped into a lot of like Rydberg atom settings and things like this. Like Rydberg problem template, I think is what we've got it called. But we've got a few of those in the works for different settings. Yeah. Effective models and full models. Yeah.
And I have a question about some design decisions. My main one really is, have you considered quantum optics JL versus quantum toolbox? What in the trade-off was making quantum toolbox preferable?
So the quantum toolbox package is very cool in that they are trying to like duplicate perfectly Qtip from Python, and like so many quantum people are using Qtip that to give them a Qtip basically interface in Julia is maybe one of the most quickest ways to access that community. Also, they're involved with the Unitary Fund as well. Yes, quantum optics is super cool. We are probably would love to allow for both packages to be accessible. Like ideally, we could allow any like quantum objects from either of these packages to just like be converted into quantum systems. Because like the real use for this is like basically building the Hamiltonians, and like where do you want to maybe roll out your system, test an evolution of your system. But the Qtip Python community is kind of why we went with that. Yeah.
I think, like to just add, like I think entry points and exit points for these ideas, like getting rollouts that like you would know like how to implement the right kind of rollout, how it would tap into our framework, like whether that's like the way to go to allow for kind of users to specify if it's going to be
Thank you.
Any more questions?
Do you think that I could use Piccolo JL in the future to test if like a hardware-specific mapping, which I create like for a specific circuit, has a higher or lower fidelity than a different one, or is that out of scope?
So you're saying specifically like if you were to implement a gate, like you have a Hamiltonian model and then you're trying to integrate this into a circuit and then roll it out in a circuit setting. Like some of the work that we've done, we partnered with IBM to kind of like build on top of their Qiskits, like Qiskit dynamic simulators and stuff like this. And I know Qtip has a like open pulse circuit simulator that sort of allows you to plug in pulse implementations. The first talk, and Yao and others, having like basically circuit level implementations and being able to plug in kind of like pulses, introduce coherent add all that infrastructure would be really nice. So I don't know when we would start kind of that pipeline, but like having those features would be awesome. And I think there's a lot of really interesting research questions and like practical applications to building that. So.
Also, like in this framework, which is something that's like very interesting is if I go all the way back here. So if you have some like hardware parameter, that would basically be like a parameter that propagates into a model Hamiltonian. You could throw that parameter into this problem and optimize over the parameter itself. which would tell you what parameter you should use on your hardware. So you could basically solve a big problem where you have like some constant parameter in here. So like we have some ideas right now we're working on with like kind of adding in like a carrier wave frequency for like for one of these pulses. But like pretty much a device parameter you could throw in here as long as it propagates into the model, solve it, and the solver will tell you what device parameter will give you the best result. And solve for the pulse jointly. So it'll solve the whole problem in one go. So that is like something we can totally do. We don't have the tooling right now to do it, but we're very interested in doing this.
Because back when I started using Julia, it really wasn't good. Nowadays,
So I'm not sure how to put this properly in context, but like, is everything Hamiltonian based? Because in general, in quantum problems, you can also consider wave function deformation. And so do you always need Hamiltonians for your package?
Everything is built around these operators, which depending on like the underlying integrators, we sort of make some structural assumptions to like add benefits, which is kind of what JuliaCon's last year's talk was about. But that doesn't mean that you couldn't change the integrators, and we've done that to explore other kinds of problem classes like more traditional like quantum chemistry or just kind of like spatial, for example, wave functions. So we have like quantum states that are embedded into the 0, 1, 2, 3. But like we've explored these. I'd say that's still a work in progress for us to decide how these integrators should get most flexibly introduced into this framework. But we've done some problems for this. We just don't have maybe the stability to like release it in the public code. Yeah, it's just not quite there yet.
Yeah.
But would be happy to talk more about what we've done and kind of like, what's missing.
And I think in this framework, what's cool is like the states are variables themselves. So you can like, if you want to put some constraints on like the shape of your wave function or something like this, work in a spatial domain, all of that is very possible in this framework because of the direct nature of the problem. Yeah.
Thanks.
Okay, thanks Aaron and Pickle team again. We'll have the next talk from Stefan.
Beautiful. Thank you.
Yep.
Everywhere.
Okay, so hey everyone, my name is Stefan. I'm a professor at the University of Massachusetts, Amherst, and I'm also part of the Center for Quantum Networks, which is a big NSF engineering research center, one of those hopefully 10-year programs with a singular engineering goal. The center is pretty big. It includes SCORE partners, Amherst, Arizona, and a number of other institutions. It's really hosted at the University of Arizona, where a lot of quantum networking hardware is being developed, together with a test bed being developed in the Boston area. And a lot of the topics I will be presenting today are focused on the virtual test bed we're developing for the center, which to great extent is used to try to inform, predict potential bottlenecks, what in the hardware needs to be focused on. That's on the low-level hardware side of things. And also it's a tool that today can be used by a lot of the CS folks that don't necessarily care much about hardware, but they're really interested in designing networking protocols for a potential future quantum network, and without having to worry about boring details like how do you actually build NV center-based repeater and so on. So with that, I also want to mention that the center has started a mini grants program where we're funding development on bug bounties, summer of code style projects. The goal is sure to help building out the software, but also to build out the community and to teach junior developers how to not just do good math, which probably they have already learned in their grad program, but also how to properly contribute to open source, how to do Git pull request and so on. So if you're timid about that type of skills in your toolset, don't hesitate to start contributing. We're committed to helping building a next generation of competent collaborative programmers. So with all of that out of the way, I'll start talking about the stack that's being developed by the Center for Quantum Networks, and then focus on the software tool I mentioned. And then I'll specifically discuss some of the networking protocol development APIs we're building. So in terms of what you need to build a full quantum technology stack, you obviously need materials which exhibit some interesting quantum properties on a scale that's engineeringly useful. On top of that, you need some form of analog control, for which you probably should be using Piccolo. On top of that, now that you have some form of some form of analog control, you want to start pretending that you have a digital system so that you can start building scalable machines. Well, those noisy digital circuits that a tool like Piccolo can generate then need to be built into actual error correcting codes and whole error correcting schemes. And we also had presentations today on that type of technologies. And finally, when you have all of this, you can start talking about applications and algorithms, or in the context of the Center for Quantum Networks, it would be more network protocols and applications in terms of networking, communication, and sensing, not necessarily just computation. And to help with some of the design work on our end, we've started building a full stack design and optimization tool. The requirements we have for the tool are quite diverse. So we do need some form of symbolic description for quantum logic, and that and a number of other components were discussed at the previous JuliaCon, actually. So we already have a very humble, small symbolic core that lets us express algorithms and protocols in a backend independent way. Similarly, we are building a declarative noise model database so that you don't require everyone to submit a gigantic super operator just to model their error processes. All of this is meant to be translated to a diverse set of backend simulators. So while the front end is symbolic, the majority of operations, the majority of the simulation happens numerically. And for some situations, we want to be able to model gigantic error correcting codes over thousands of qubits, or purification circuits over many thousands of bell pairs. And for a situation like that, we'll be using a Clifford simulator. So all of the symbolics will be translated to a Clifford backend. For other situations where we are focused more on analog noise, we'll be using wave function simulators. And we're building also conversion utilities between those two if someone wants to work in the same situation with some low-level control that's then used for some large-scale purification network. Because a lot of this is focusing specifically on networking, we naturally need a discrete event scheduler, which has been a frustration because in Julia or really any other language, those are fairly immature tools. That's probably also some interesting sociology questions here. Why is this type of tooling not as mature as many other libraries we have available? And a goal here is also to make this very Lego-like, so that a network scientist can use it without having to worry about low-level hardware and vice versa. So, with all of this out of the way, the software tool is called Quantum Savory, more or less a joke on the SPICE classical electronics simulators, also the best SPICE you can get in the Balkans. And I want to focus on what we're doing in order to make network protocols composable. I want to spend a minute to defend the idea that we're even caring about quantum networking. The application is not as immediately obvious necessarily as quantum computing, so I want to just to set the stage for that. So imagine Alice has a qubit, Bob has one too. Those qubits can be correlated, and then they can be correlated in ways that are not possible classically. If you list the possible correlated states for a classical system, you won't span such a basis of 4 different states. You have much more richness in terms of available correlation in the quantum case. And I won't go in detail through this, given the audience, that's probably fairly obvious. But a few years ago, I participated in setting up an art installation that explores these ideas. It was a fun setup that I encourage you to look up. It was at the Yale Quantum Institute. You were basically walking through a large dilution refrigerator, and depending on your location, you were making non-commutative projective measurement, and it was a way to teach the public about non-commutativity and hidden variable theories. But what can we use these non-classical correlations for? So one of the obvious hyped up applications is in security with quantum key distributions, but there are much more interesting ones as well. This type of correlation provides you with a trade-off between bandwidth and space. Basically, in advance, you can store in memory bandwidth that you can then use when the network is congested. Something not available classically. The quantum primitive to use here would be something called superdense coding. Similarly, you have new types of sensing here that can go beyond classical limits, again, thanks to the sacrifice of entanglement. There is the more mundane application where you're networking existing quantum computers. And sure, maybe that won't necessarily be interesting when you're talking about large-scale networks, but modular hardware in the same fridge will need its own networking protocol as well. And lastly, one of the main reasons we should care for this scientist is that nature really doesn't like this type of object existing. And if you're able to create something that's so unnatural, you probably will be building technology that's applicable in many other domains as well. The finesse necessary to build this type of states does translate into better technologies in plenty of classical applications. So let's go through a case study of a typical networking problem in which if you use most of the available tools, you will start having a lot of frustrations when you're trying to build something large and composable. Let's focus on the need for repeaters, the repeater chains on a large network link. So in fiber, you have, or really any other media through which you'll be transmitting a qubit, an optical qubit, you have exponential loss. And that exponential loss puts very hard limits on how long a link can be if you want reasonable fidelity or reasonable rate for the established entanglement. So a typical solution in such a setting is to set up repeaters in which you perform some form of, it's called entanglement swaps. So in this animation here, we have, let's see, 5 repeaters. Every repeater has 2 slots. And all that these repeaters are capable of is establishing entanglement links between neighbors. You cannot establish a link from here to here. The loss at such a long distance will be just too prohibitive. On the other hand, you can in parallel establish links between neighbors. Those are much shorter links, so the loss is by far not as damaging. And there is an operation in which, called an entanglement swap, in which locally you interact with your 2 halves of 2 different bell pairs, and that extends those 2 bell pairs into 1 long bell pair. This is the entanglement swap protocol. Here you can see that frequently here we have 2 bell pairs in this direction and in this direction, and the swap basically makes them span this whole gap. And you'll be doing this at each register until you have a long-range entanglement that you will be consuming, and in this particular simulation we have a plot of latency versus quality of entanglement for the whole link. So how do you actually program this? How do you model this in a real network? In our setup, the goal is to make it as simple as possible. It's nothing more than setting a couple of different networking protocols that somehow work together in a composable way. And discussing how to make it composable is my main goal here. But just to showcase the simplicity, we just run the start of a process, of an entangling process between on each edge of the network. And then we start a swapper process at each node, and an entanglement tracker process that tracks the metadata necessary for these basically classical communication protocols that govern the quantum network, also at each node. And it's not an exaggeration that pretty much this is all you need to create a plot like this in our simulation tool. So design considerations that we're facing here is that we need something that lets us track all the classical messages between these quantum nodes in a way that's scalable, in a way that doesn't require bespoke code every single time you add some new networking dynamics. And in particular, these 2 protocols that are running on each node, they need to communicate with each other. How do we set up this communication so that we are not overwhelming the developer with special cases? Well, let's run through an example of this protocol in the abstract. We have Alice and Bob, which are the end nodes, and we have a repeater in between them. The repeater will establish a link with Alice and a link with Bob, and some classical controller will then know locally that Alice will know that she's entangled to the repeater will know that they're entangled in one way to Alice, in another way to Bob, and Bob will know that they're entangled to the repeater. The repeater then will detect that they now have an opportunity for a swap. They have 2 halves of a bell pair, 2 different bell pairs in 2 different directions. They'll perform the swap, but then they will need to tell Alice that, hey, Alice, you're not entangled to me anymore. You're actually entangled to Bob. And the difficulty is tracking this type of messages when you really want to build a large network that's not necessarily one-dimensional. Even in the one-dimensional case, if you have a chain of repeaters, it starts getting pretty annoying because, sure, repeater 1 is entangled with Alice and repeater 2. They perform a swap. They tell Alice. They also tell repeater 2, but by then, repeater 2 also had prepared to perform the swap, and repeater 2 is not entangled to repeater 1 anymore. The repeater 1 and Bob are the ones that were entangled after this swap at repeater 2. So messages will need to be propagated through the network as well. And you will need rules for that, different protocols for that. And most annoyingly, you would want those protocols to work even if you are running a ton of other processes that might be congesting the network or fighting for resources. So what do we need from such an API? We need some metadata for describing each node's local knowledge of what the network as a whole looks like. The node's belief about what their entangled state is, and anything else about the state. It doesn't need to be just the question of entanglement. We need some way for nodes to be querying this local metadata, to search through it, to decide whether they're at the stage at which they can perform something interesting, like, for instance, a swap. We, of course, want to have visualization tools for that metadata. And most importantly, we want composability of these protocols and of this API as a whole. And again, when I was talking about these protocols, I mentioned a couple of times, it won't be just swaps. This was one example. But at the same time, you might be running super dense coding between two nodes of the network. You might be running teleportation of logical qubits on top of which you're running some form of error correction, beneath which you're running some form of entanglement distillation. The entanglement distillation will be fighting for resources with the swaps. The swaps and the distillation will need to be scheduled with respect to each other. There will be a lot of frustration in sharing of resources here. And the state of the art in the existing tools is kind of, if you compare to the classical internet, where every single protocol, every single application protocol like Skype and Zoom and web had to have its own packet type in the networking layer. There is truly no separation between application layer and networking layer in the current simulation tools. And you cannot track resource congestions in a viable way with current simulation tools. We believe that we have the first steps to a reasonable solution here, basically a way to track metadata where you don't need to hand stitch every single protocol, where you don't need to make bespoke changes to protocol A if you want to implement protocol B, which is the current state of the art, basically. We want to have the composability that Julia enables in many other domains. So we're setting up a pretty simple tag and query API. So in the next few minutes, I'll just run through an example of how this API is used to implement the aforementioned protocols in a more composable way without having to explicitly create links between the protocol processes. So we'll be able to record some form of metadata. For instance, in the entanglement protocol, we'll be tagging this is the protocol that creates the initial row bell pairs between nearest neighbors. We'll be tagging locally the slots that are entangled with some form of metadata. Here, we've decided to call that metadata the entanglement counterpart struct with some fields that describe exactly who you're entangled with. What is the other node you're entangled with, and on that node, which specific qubit register are you entangled with. There's a couple of simple add-ons here in terms of pretty printing and pretty visualizations, where Mackie immediately gives you that metadata when you hover over the qubit. You can see that this particular qubit, the classical metadata describing this qubit, that's stored completely separately from the quantum state, does tell me, the controller of this local node, that I have a belief that this qubit is entangled to some other node. We also will need a couple of other tags, like we'll need an entanglement history tag. If a swap happens, the node will not have entangled qubits anymore, but the node will need to retain knowledge that there were entangled qubits here that I swapped, because later down the line, the node might receive a message, hey, I did something with my half of the entangled qubit. And you will need to propagate that message. And that's a particular example for swaps, but it scales to other types of protocols as well. Similarly, if a swap is performed locally, I will need to send to the remote nodes an entanglement update message. Again, the names are arbitrary, but roughly the type of metadata you need to store semantically would be the content of where the swap happened and how you need to update your remote belief about who you're entangled to. Well, that's for storing the metadata. Then the more important part is really querying the metadata. For instance, the entanglement tracker it will be one of the controllers that updates the metadata when they receive messages from remote nodes telling them that, hey, I've performed a swap, you're now entangled to someone else, not to me. So the entanglement tracker will need to query locally for entanglement history data, and importantly, the query needs to be capable of wildcards. So you can put these emoji question marks in the query function so that you can find all tags that map the query up to a wildcard. So here, these are specific values that you need to be exactly equal to in your query. But these are values that can have any value. And similarly, you also have access to predicates. For instance, here, this would be in the swapper protocol deciding whether to perform a swap. And they will be checking whether they have two entangled qubits here. This is checked for one of the entanglement components. And there might be a predicate for, hey, check whether the coordinate of the node I am entangled to is to the left of me, thus ensuring that there's some directionality to the repeater. Again, we have access to wildcards, and we have access to other metadata about the qubits, whether they're locked by other processes, whether they're assigned, and so on. The details don't matter too much. The overall idea of tagging and querying, though, is what permits the composability here. And this enables much more sophisticated protocols as well. So I'll run through one or two pretty examples, and then I'll open up for questions. For instance, here's an example of quantum switch. The way we define it in this context is that we have some star network where we have a center switch, and we have many clients. And a client wants to be entangled to another client. They'll make a request to the switch to, hey, please entangle me to this other client. But all the network is capable of is creating entanglement between the clients and the switch. The switch will need to perform one of those aforementioned swaps. Here, again, we have a set of tags, of packets that announce, hey, I'm requesting this resource from you. The switch is querying what the currently received packets. The switch is also querying what is the current state of entanglement that's available to it. It performs some interesting graph optimization problem internally, and then it sends out tags saying, yes, I'm attempting this type of communication. You'll be the first to fulfill your request. And the simulation tracks the backlog of requests and so on. You can change the request rate between every single pair. If you globally change the request rate to be very low, you see how this is a plot of the backlog over time. The backlog starts dropping. So it lets network scientists compose many protocols and study their performance on real models of hardware without having to learn anything about the low-level models, and without having to write bespoke protocols for every single simulation. Okay. Yeah, and again, the simulation overall is just a set of processes that make requests between each pair, a set of processes that track entanglement at each node, and one process, the entanglement switch in the central node. Of course, the switch process itself is pretty complicated internally. It has a ton of optimization routines in order to decide which link to be fulfilled first. But in terms of communicating with other protocols, it just uses one or two queries, and it just uses one or two tagging functions. This is another example of repeaters, this time on a grid, where we want to connect this node here and this node here. But again, we have only direct links between nearest nodes, and the simulation runs with exact wave function simulation, although we have many hundreds of qubits. Because the entangled pairs are never more than 4 qubits, we don't need to worry about scalability. All of the nodes have concurrent processes running on them, and the entire simulation was again This whole thing was generated in maybe 10, 20 lines of code because we have these visualization tools and because we have these composable protocols. Sure, the code to create the protocol is not necessarily trivial because there's some protocol logic to worry about. But as I mentioned, the protocols are composable because their communication with the other protocols are nothing more than a couple of queries and a couple of tags. And with that, I'll be closing. I want to mention again that we're running since last week a lot of bounties, both large-scale Summer of Code style projects for more advanced developers and small bounties for people that want to have their first taste of open source development. We're also hiring contractors for a lot of this work, including potentially part-time, remote, worldwide. And on the more academic side of things, we're hiring both graduate students and postdocs. So message me if you're interested. Amherst is very pretty and bucolic. And that's all I have.
Any questions? Yeah, thanks. Very interesting talk. I have a high-level question, maybe. So if I'm thinking about routing in standard network protocols, right? There's of course tons of algorithms out there, but they make certain assumptions about the network, and I can definitely see these assumptions not satisfied in your setting. Like, you know, especially when I think about noise and potential noise correction and so on and so forth. So, I mean, you showed this example with a switch, but now scaling this up a bit, have you thought about the sort of the underlying optimization problem, the routing problem? Is there something that's in your head, and you can say a few things about that?
So I would say that's a type of research program that problem that people in the CQN want to solve. Some of them purely theoretically, some of them with a tool like this. The current workflow in the center is usually you have a lot of classical networking folks that have some extremely abstract definition of a network, maybe large, maybe small, and they solve something within their context. They make proofs about stability of the network, proofs about scalability, proofs about amount of overhead for some type of communication or congestion or whatever. And then they go to the CQN Summit, they present that, and the experimentalists don't engage with it because to them this is so incredibly unrealistic. A tool like this, the goal is really to make it possible for these theoretical proofs to easily be then turned into a simulation that can be verified in a way that's informative for the experimentalists, that do take into account much more about the hardware. So here I'm describing the use of this tool more as a way to vet a theoretical protocol. In the opposite direction, I think, is more closely to what you asked. You implement the protocol and you're running some form of optimization. This is much more nascent in terms of what we have here, but we are already working on tools related to stochastic AD so that we can do some form of gradient descent over the stochastic processes that are running on the network. But that's right now pretty experimental, not really part of the bigger software as a whole. And then there are all the more naive ways to do optimizations. The tool is scalable because of the modeling techniques we have put in. So you can do the naive thing of running a few thousand simulations and just varying parameters. It's just that, sure, it works, but it's not something to brag about.
Any more questions? Okay, if you no more questions, let's next step.
I could ask one question. I don't know if you could speak to like what the current state of like the hardware infrastructure is. Like at I know Chicago has some, and you mentioned Arizona. So I don't know. I'm not up to date on where we're at, but I know distances are getting bigger and stuff like this.
Very quickly, because I imagine I'm running out of time. The Boston testbed is meant to be technology demonstrator over long range. So there is Lincoln Lab, MIT, and Harvard are connected together with a single fiber that's occasionally in bad condition. But now they are demonstrating various forms of entanglement distributed over these, I think, tens of kilometers of links. Then the Arizona is a campus-wide network. It's a much smaller network, but it's meant to be a system integration hub where you're not demonstrating long ranges, but you're demonstrating that you can actually build 20 nodes together, even if they're closer. So it's much more about the engineering difficulties of building a real system. So yeah, you probably know the term integration hell.
Okay, let's thank Stefan, and we'll have a short break. Our next talker will start at 3:40.
In terms of the schedule, we can easily do anything between an hour and a half, right? And we're also running hackathons, and we do have funding for some bounties for the hackathons. So if you have something like, hey, here's a hacking toolkit, and we want extension package for that, we can do something like that as well.
That'd be awesome. Yeah, we just got through the unitary hack, and I think we like first started trying to like open up and think about what it looks like to create sort of the right lead-in issues that are like, okay, this gets you started, and then you get interested, and there's actually like three more issues. So yeah, so we like have thought about that. So that's really cool.
There will be 4 people from the unitary fund technical staff that will come on Thursday, and they will stay until Sunday. They will actually be running their own workshop for the entirety of
So
Saturday.
like Nathan and
Yeah.
yeah,
Yeah.
okay.
And that probably means that you probably can join when they're there as well.
Yeah, so we would double tap you. We would give some collaborators.
Probably in terms of scheduling something that works with the unitary folks would be afternoon of Thursday or anytime from Friday.
Sweet. Were you coordinating with Callie by chance?
Yeah.
Okay, yeah. If you want to set us up on email or something, like
Yes,
we know them all super well. So.
Perfect.
Yeah.
Do you can you give me an email?
Yeah.
Do you want to just write something down?
Yep. I just noticed there's paper there. So.
Yeah. I was looking for a pencil. No problem.
Oh, here you go. I would solve the wrong problem for you.
Perfect.
Try to be very careful with your miserable.
Yeah, I mean, they're writing cursive.
on physics-informed automatic differentiation.
Thank you very much. I am Niklas. I'm a mathematics PhD student at EPFL in the first year in the Mathematics for Materials Modeling group with Professor Michael Herbst. Right, let's get into it. Physics-informed automatic differentiation. What is it? Quick disclaimer in the beginning. For this talk, since I have only 10 minutes, I thought I would basically skip all the math and just show code and pictures. But if you're interested in the details of any of this, there's like a lot of interesting math behind it and a lot of interesting programming questions too. Like, do get in touch. Let's talk about this. And there's also the hackathon on Thursday. Let's get into it. Right, physics-informed differentiable programming, PDE. There's like many of these terms floating around. I see it roughly as an umbrella term of a combination of you use automatic differentiation. You want to use scientific models that use partial differential equations, potentially very complicated, and you have to use numerical methods because there's no other way of dealing with partial differential equations. So, and then if you can get derivatives through such methods, these are of course interesting for many applications. There's many talks about this here at JuliaCon. I'm sure you know inverse problems, uncertainty propagation, there's optimization, a lot of different stuff you can do with it. Right. So the key ingredient is this derivative, and it's not such a trivial thing. So the question is, how do you get such a derivative, right? Since physics-informed is in the title, and we do work on DFT, density function theory, in solid-state physics in particular, I want to start with a physics example. Here's a lithium crystal, as you might find it in a lab, freshly cut. Let's skip to the atomistic view. This would be a perfect crystal. An idealization would be such a periodic arrangement of atoms. This is what's called the body-centered cubic crystal formation, and each of those would be a lithium atom. The bonds here are just for illustration. It's not really computed like a graph. And you would set periodic boundary conditions to get away from like surface effects. All right, a comic way to think about density function theory as a complicated PDE, there's some kind of physical parameters for a given structure. There's the structure itself, then there's physical parameters, and these together somehow make up the environment in which the PDE is solved, and this determines the solution of the PDE, in this case rho, and then from that solution you might either look at it, but usually then you're post-processing that solution and computing some kind of observables. In DFT, for example, so we are interested in the total density of electrons, and then quantities of interest might be energies, forces, band gaps, stuff that gets you closer to something you can measure at a large scale, basically. Right. So there's some of these parameters that are interesting for inverse problems, for example, are first of all the arrangement of the atoms, of the nuclei. This would be the lattice and the positions of the atoms, but also what their type is. And this would be, for example, to do geometry optimization to find the ground state, to even determine that such a crystal would be the minimum energy configuration. But there's also two other kinds of that come to mind. First, one of them is pseudopotentials. It's a very interesting topic, and I'm actually currently working on it, but I don't have time to go into detail here. And another one is the exchange correlation functional. Yes. But last but not least, there's also numerical parameters, right? You have to choose your grid size and the tolerances of your iterative solver, and you also have to choose in what kind of arithmetic you're solving this, right? How many bits are you using, and so on. And so these two are kind of always clashing with each other, which is why numerical analysis is so interesting. Right. In code, so what I'm doing here, I'm loading the physical system here from a file that gives me a cell consisting of a lattice, atoms, and positions. In this case, there's just a single atom, and the lattice is a 3x3 matrix describing the periodicity. Right, looks like this. There's a 3x3 matrix describing the periodic arrangement. There's just a single atom, which is lithium, and its position is at 0. What we do here is we create a supercell that would look like 2 atoms with periodic boundary conditions, and then we choose a bunch of numerical parameters here. One I will talk a bit, I will show examples with increasing the energy cutoff in particular, which you can think of a grid spacing parameter, very high level. Right. Then once we have our system, this is a forward model that would solve such a system, giving these parameters. It would do a bunch of setup stuff and choose a discretization and so on, and then call the self-consistent field method, which solves for the solution of the PDE, so fixed point method. Good. Solve, converges very quickly, very good. This is very coarse parameters. This is what a slice of this 3-dimensional electron density would look like. And you would see, aha, there's 2 atoms and its periodic copies. That's the rest you see. All right, I spent way too much time on this, but I think it's important to get a setting first. Implicit differentiation would now mean that we want to solve for derivatives through such a process, but not by differentiating the process itself, at least not the numerical one. We want to differentiate the physical process, right? We want to differentiate the equation. So that means solving for the derivative is itself a numerical problem that should be controlled. All right. So what I'm doing here is I'm I'm doing what I did before. I'm solving for the SAF, and then I'm doing some post-processing on the solution to compute a quantity of interest. And these are the forces on the atoms. And this is I'm doing by forward diff, and forward diff is what we currently support in the package, but most of what I'm saying in this talk would also apply to reverse differentiation. And even the solver that is at the heart of this is the same solver for both cases because it's a self-adjoint system. Yes. So what I'm, sorry, 2 more minutes. So basically what happens before you perturb the system in its symmetric phase, it does not have any forces on the atoms. When you perturb the atoms a little bit, you do get forces. This is what you see here. And this in the background uses this generic autodiff solver, which is very cool. Now, since I only have 2 minutes left, I would rather jump directly to the slider, which is why this is a Pluto notebook. And what I'm doing here, I first solve it on a very coarse grid, where I say the energy cutoff is just 5, and that means it's a very pixelated image of the density. But what I'm also showing here is I'm also showing that derivative of the density with respect to the parameter in the PDE. And now I can increase the discretization parameter and each time solve again what the correct notion or what the correct form is of this gradient. And just by playing by this plot, this is kind of the point, high-level point I wanted to make. Derivatives themselves of PDEs might have complicated structure, and here you see it looks as this one is even a bit more complicated than the original density itself. So it's something to think about. And whether this matters for your application or not is then also an interesting question. With that, there's a bunch of more stuff I could show, but just talk to me about it. There's something interesting with crystal symmetries and symmetry breaking, and there's very subtle bugs one can have. And there's also clear ways to avoid it. Tomorrow there's the 5 years of DFTK talk by Michael, which is a longer talk, and there will be much more details than here. And there's a bunch of interesting further reading, and I acknowledge all the DFTK contributors, all the Julia package authors, and all of you, the community. Thank you very much.
We won't have time for questions. If you have questions, please feel free to reach out to Nicholas afterwards. Our next talk will be Liam about equivalence checking of a dynamic quantum circuit.
Hi. I was wondering, in the image that you showed, the last image was the slide there.
Yes.
If the fact that you have derivative on the left side, that would be explained by the fact that you have the right side to influence. Eventually you have a ramp geometry.
That is definitely part of it.
Yes, welcome to my talk. My name is Liam Hurwitz. I'm a master's student from the University of Bremen. This talk will be about equivalence checking of dynamic quantum circuits. It's going to be a quick talk. I'm now also working at a research institute in the DFKI, the German Institute for Artificial Intelligence. This focus, since we are the hardware architecture working group, will be more on how to have like an EDA flow, which means electronic automatic design. So what are the big limitations of current quantum circuits? Well, first of all is the limited amount of qubits. Like IBM has 1,000, but there's still a very shallow coherence, so the qubit states decay very fast, and the gate fidelity is very low. Yes. We can solve this by IBM tries to solve this by introducing a new type of quantum circuit called dynamic quantum circuit. The important thing which happens here is that, first of all, they recycle qubits. So here we see a Bernstein-Parsilani circuit with 3 qubits, and this can be converted into a dynamic circuit which just has 2 qubits. Here you see that this one is actually this qubit, Q1, which is now moved here. And further, we can introduce further non-unitary operations, such as active reset you see here, or if-else, and mid-circuit measurements. So this motivates the case for why dynamic quantum circuits are important. To reiterate, they solve one of the biggest platform limitations of current quantum computers, and in the best case, they have an n to 2 reduction of qubit that's bounded by the number of entangled qubits. So next, why is circuit verification or equivalence checking important? Well, if you show me 2 different circuits and ask me are they the same, this is a very important question, like if you're designing circuits, since we all need to know that if we optimize something, the functionality remains the same. There's a naive way to test this, which is by doing a proof by negation, so just trying every input and seeing that every input generates the same output for both circuits. This has a bad time complexity and a bad space, or size, like it's both is exponential. We want to use the power of reversible operations, so I think you all know that quantum circuits are unitary, and thus we know if we have one and the adjoint of itself, we get the identity. This is what I'll be using. Here we have an example of just 2 C0 gates put after each other, and I say this is equal to an empty circuit. You can prove this by having the first matrix multiplied with the second matrix, and this will be again that. Again, bad complexity, exponential runtime, and cubic runtime and exponential space. ZX calculus is one good way how to solve this. It is a graphical way how to describe circuits. The circuits are described by wires and spiders. You can read my paper or the slides or the Pluto notebooks to get more details. What really matters is connectivity is the only thing which matters. So this is actually equal to this because we just go from here to here, so it doesn't matter if the lines are bent or straight. Most important for ZX calculus is that rewrite rules do not change the unitary map or the linear map as they're called here. So for example, if we have two phase changes, we can just sum the phase changes into one, or we know that 2 Hadamards is equal to this. And by applying all of these rewrite rules, my software also has them in the non-terminating way, but we just stick to these. By applying these rewrite rules, you can take the one circuit and the adjoint of the second one and just rewrite it or simplify it using circuit optimization algorithms. So to prove identity, we just show that we are remaining with bare lines. Here's a small example. So if we have one C0, another one, and another one, this is actually equal to a swap gate. We can prove this by first twisting this one time. It's a movement like this. Then applying the balance rule and the fusion rule. And then we immediately have proved that this circuit is equal to this gate. Next one, now what about non-unitaries? There are different ways. I decided for my research to do a unitary reconstruction. So given a circuit which is dynamic and contains non-unitaries, such as this reset or the classically controlled logic, I can overcome the resets by undoing the recycling, so moving this back into a new qubit. This is okay, because this runs on hardware, which is constrained by platform limitations, such as the qubit count. This runs on my classical computer, which in the ZX calculus.ja module, which is very efficient, is not limited by a high amount of qubit. Then I move all the measurements to the end, thus having again a unitary circuit. Here's a small example of the Bernstein-Vasirani circuit. The already reconstructed unitary part, which I merge together here. Then I apply all the rules, and I'm left with only empty wires. Thus, I prove the equivalence between the circuits I showed at the beginning of the presentation. How is this done? First of all, there are many nice libraries from the Yahoo ecosystem, which I'm using. Thank you very much to everybody who contributes to them. Yahoo.chasm, OpenChasm parses it. This library I developed myself, and it soon will be published. It does the unitary reconstruction, and next I will implement the optimization steps. Then it's converted into the high-level intermediate representation, into the X calculus, and then we verify the equality, using also a method I implemented in zxcalculus.jl. There are like 7 notebooks I wrote in the different repositories, so check them out. They're linked also in the pre-talks. Ask me about more, and please ask questions now.
We have 2 minutes for questions. Any questions?
Hi, great talk. So the input circuits, they have to be in like a CHASM string format? There isn't like a symbolic language you've made to specify the input circuits?
I use OpenChasm files since there are many benchmarks that contain thousands of circuits, and my goal is to have like a complete EDA flow. So load the circuits and bring them in. Of course, you can also directly work with ZX calculus, where you have the push function, where you can push specific spiders onto it, so that should be possible to do it symbolically.
Sure. Because one application I can imagine is you've got a circuit in a conventional gate basis, but you want to check whether it's equivalent to like your really funky esoteric circuit expressed with a weird basis, which unlikely is easily representable in QASM. So would you consider like making support for like many controlled power gadgets or something?
Should be possible. Also, Catherine will be having a nice talk about OpenChasm 3. Which I'm not supporting yet, so I'm looking forward to that as well, and we should talk after that talk about
Sure.
this.
Thanks very much.
Thank you. We will have our next talk. Thanks, Liam. Let's welcome Joseph from Flatiron about I-tensor networks.
Brilliant. Yeah. Thank you for listening, guys. So yeah, I'm going to talk about a new package that we've been developing at the Flatiron Institute in New York. So the Flatiron Institute is a research institute in Manhattan. It's part of the Simons Foundation, and within this institute, I'm based at the Center for Computational Quantum Physics, and our mission at CCQ is essentially to develop algorithms, theories, and code needed to solve the quantum many-body problem, which, as I'm sure you all know, is a very hard problem to solve. And this talk is going to be about a package that we've been developing lately called I-tensor networks to try to tackle certain aspects of this problem. And as it's a talk about tensors and tensor networks, it makes sense to introduce some visual notation. Just as a little refresher, so a tensor is essentially just a high-dimensional array. It's a multi-dimensional array with some number of indices. And we typically draw them like this, just a little box with these dangling legs, and each of these dangling legs are indices. A tensor with one leg is a vector. A tensor with two legs is a matrix, and so on and so forth. And we can kind of write down algebra for these tensors in this visual notation just by connecting the lines between tensors to imply summation over some index. So this middle one here with these two rank 2 tensors, I don't know if there's like a pointer or... No, okay. So yeah, these two tensors in the middle here, maybe I'll just properly point it out. This is the contraction of two matrices together. And you get another matrix, you get another tensor with two open indices. And tensors are very important because they appear absolutely everywhere. And importantly, tensors with a lot of indices also appear everywhere. So one of the kind of big settings for these objects is the quantum many-body wave function. You have some number of qubits. Maybe you have hundreds, maybe you have thousands. Each of these qubits could be in some state up or down. And the coefficients of the many-body wave function can be seen as an enormous tensor with an index for each of these qubits. And this tensor essentially encodes all of the amplitudes for the wave function, so it has like an exponential amount of information in the number of qubits. But the tensors, high-dimensional tensors, also appear in classical physics. If you look at the partition function and you kind of look at the Boltzmann factors, essentially it also can just be seen. You could take all of those Boltzmann factors and put them in a very high-dimensional tensor. Or more generally in mathematics, if you think about just a continuous function, you could do a binary decomposition of a continuous variable, and then essentially you could encode all of the possible values of the function in a tensor with an index for each of those binary digits. So you could store all of the values of the function on like an exponentially fine grid in a tensor. So tensors come up everywhere, and what a tensor network is essentially a way or an attempt to take this tensor, which has an exponential amount of information in the number of indices, and compress it into a network of smaller tensors which are implicitly contracted to reproduce that original tensor. And the advantage, if you could achieve that, is obvious, because you take something which has an exponentially large amount of memory in the number of degrees of freedom, and if you can find a series of interconnected tensors with a finite rank between them, then you essentially achieve a polynomial representation of that information. So you've gone from exponential to polynomial which is huge. That's a brilliant thing to be able to do. And it turns out that there are actually a number of problems where it's possible to do that. One of the kind of original ones which motivated the field of tensor networks was in the context of many-body quantum physics and showing that essentially the low-energy states of one-dimensional quantum systems, the wave function can be put into this format and essentially represented with only a polynomial number of degrees of freedom. More generally, people think about this in the context of mathematics and take certain tensors and construct these one-dimensional, what they call quantix tensor trains, and show that certain mathematical functions can also be encoded into this very low-dimensional space. And nowadays, kind of since in the last few decades, since these ideas came around, tensor networks appear all over the place, not just in quantum physics, not just in representing functions, but actually in solving a whole host of complicated problems, whether that's solving differential equations, solving KSAT problems, modeling diseases. And again, that's because high-dimensional data comes up everywhere. And so, you know, if you have high-dimensional data but you don't know how to deal with it, maybe a tensor network could be the way to go. But there's a slight caveat to this, which I would say that most of the success in working with tensor networks and solving these problems comes from one-dimensional tensor networks, i.e. tensor networks where the tensors are just arranged in a line. And there's good reason for that. You can efficiently contract them, so you can efficiently compute properties from them in polynomial time. It has a one-dimensional, you know, a path graph has the lowest coordination number of any connected graph, so the individual tensors are very low memory. You can prove that for certain problems it's a very good ansatz. And kind of in terms of coding, it's much easier to code up this kind of tensor network than it is to code up something much more general. And this is why a lot of kind of the state-of-the-art tensor network libraries really focus on one-dimensional tensor network algorithms. And when you go to more general tensor network structures, where, say, it's some graph of connected tensors, you come across a lot of difficulties. If there are loops in the graph, you can't even contract the thing efficiently. You can prove that certain problems are P-sharp hard in terms of contracting loopy tensor networks. Higher coordination numbers mean the individual tensors take up more memory, and it's much harder to code and reason about these objects and write a code that could work with these objects. There has been quite a lot of significant research on two-dimensional tensor networks, sometimes called the projected and tangled pair state. And I think it's kind of funny, actually, because you have all this brilliant work in 1D, and there's been this brilliant work in 2D. And I think people kind of thought, okay, one-dimensional tensor networks work brilliantly. Let's try some 2D problems with 2D tensor networks. But it turns out the 2D tensor network is probably one of the hardest tensor networks to deal with. And it's probably, it's sort of like jumping from the easiest tensor network to deal with to one of the hardest. And so at CCQ, we're starting to think a bit more generally, okay, let's not think about specific geometries. Let's think about more abstract tensor networks. And maybe try to move from 1D to tensor networks that are still relatively easy to work with, but a bit harder than 1D. And take it a bit more slower and a bit more gradually than just jumping into two-dimensional problems. But in order to work with general tensor networks, you need a lot of notation and kind of need to code and reason about it the right way, and this is what we're trying to do. We kind of think in terms of graph theory. Our tensor networks are just graphs that have data on them. We're trying to use more generic programming based on interfaces and abstract types. And we're trying to take inspiration from places like computer science, graph theory, statistical physics, where people generally consider more generically structured problems and don't necessarily impose the constraint of, I'm thinking about this lattice and I only want to solve the problem on this 2D lattice. And so within CCQ, tensor networks have been, is one of our focuses and has been for a long time. And we essentially have this whole iTensors ecosystem, which is a Julia ecosystem full of many different packages, all based on tensors and solving problems with tensors. And at the roots of these tree is the iTensors library, which is a library that has been in development for sort of over 5 or so years and has many, many contributors, and is essentially based on this idea of the iTensor. So it's just a single tensor with some number of unique indices that are that have unique identifiers in the code, and that you can do algebra with. You can contract, you can SVD them down, and so within iTensors is a lot of code for essentially working with these tensor objects and doing fundamental linear algebra operations with them. We've also been building up some graph-based code as well. So essentially named graphs and data graphs, which are wrappers on top of graphs.jl, and essentially allow for custom vertex naming, and importantly, graphs which host data on the vertices and edges, and that's exactly what a tensor network is. It's a graph with itensors on the vertices. It's as simple as that. So these are kind of like the roots of the itensors ecosystem, and then higher up we have more applications of the code and libraries for doing a whole host of things, which I won't talk about in detail, but there's itensors NPS, which is a state-of-the-art library for doing matrix product state-based algorithms. So it's very stable. It's been in development for a long time, and it's I would say it's state-of-the-art. It's efficient. It's great for working with one-dimensional tensor networks. And then what I'm going to talk about more today is our package itensornetworks.jl, which is a work in progress, but essentially trying to generalize these ideas so that we can define tensor network algorithms and methods on more generic arbitrary tensor networks. And like I said, itensors is essentially built off of these two packages, itensors and named graphs. It introduces the abstract itensor network, which is just an abstract graph that essentially has methods defined for it for like pulling up the vertex data and manipulating the vertex data. And then within it, then we try to offer as many features as possible, such as building tensor networks, contracting tensor networks, gauging them, optimizing them for various problem solving. This is kind of the method that we're going with, and the kind of the structure of the library. And as I said, the coding philosophy is based on generic programming. It's based on abstract types with methods that need to be defined on them. And the idea is that essentially this library depends on external, rigorously tested libraries such as named graphs, such as itensors. So a lot of the code and a lot of the stability is based on these libraries which have very specific focuses, and then this library can build on top of them. And at the heart of this library, at the heart of dealing with a generic tensor network, is that you need to contract it. You essentially need to be able to take your tensor network, which might have a polynomial, has a polynomial representation in your memory in terms of the number of tensors, but you need to be able to query it. You need to tell me what is the value of this tensor network, or what is the gradient of this tensor network. And as I've said before, when there are loops in the graph, generically, you can show that it's P-sharp hard to do this contraction. And so what we want to offer in the library is essentially different ways to contract these tensor networks, is different ways to deal with them, whether it's exactly contracting them or approximately contracting them. So for example, we have an exact contraction backend where you can pass a tensor network, and you can ask for a sequence to contract that network. So it's all about trying to find the optimal sequence to contract it. And so itensor networks can call out to other Julia libraries that essentially have very sophisticated sequence finding methods inside them, like OM sum, contracted in orders, and IN expressions. These are all possible to query with, to call to try to contract an abstract itensor network. One of the other methods that we have, I should clarify that the exact contraction backend, finding the optimal sequence in itself is essentially, as far as I'm aware, it's NP hard. So if you give it a big enough tensor network, this is going to become really difficult and slow down very fast. So we offer also approximate contraction backends. And one of the kind of new ones on the block for tensor networks is belief propagation, which is actually a method that's been around for a very long time for performing statistical inference for coming up to 100 years now. It was introduced by Hans Bethe back in 1930s, and has kind of been all over the place in computer science since, but only recently has been realized it can be applied to tensor networks. And the idea is that you define a message tensor on each of the edges of your network and you define an update rule for these message tensors based on passing all the messages through a local node and getting a new message out. And if you run this algorithm over and over again, it will typically converge to some fixed point. And then you can approximate the contraction of the tensor network by taking the product over all of the vertices of the tensor network with the incoming messages divided by the product over all the edges of the messages and their reverse on that edges. So you get an approximate. And crucially, if the network has no loops, you can prove that this will exactly contract the network. And it will do it, if you write the right belief propagation code, it will do it with the correct computational scaling, i.e. it will contract a matrix product state as efficiently as you can contract a matrix product state. So we have this belief propagation backend in our code, and you can use it to do things like contract a whole tensor network or take the gradient of a tensor network by essentially getting all the messages coming on to that message. And we've really found developing this belief propagation code is at the heart of this library because it's geometry agnostic. The code, you can write code that is completely agnostic to the graph or the tensor network itself, and then you can just run it on any tensor network you want, which is really powerful. And if you have a tree, it will do it exactly, and if you have a graph that has big enough loops, it will get you a very good answer. But sometimes you have to go beyond belief propagation, and you can't afford to do exact contraction, so we're also coming up with new schemes. Most recently, some of my collaborators at the Flatiron Institute came up with a new method essentially based on approximately contracting tensor networks into other tensor networks. So saying I have some tensor network and I want to approximate it as a matrix product state or some binary tree, and it's a density matrix based algorithm, and there's a new paper on the side post about that. So we offer all of these possibilities in the library because contracting tensor networks is at the heart of optimizing them. And then the idea is then that we can use this code for taking the gradient of tensor networks, contracting them, to essentially write algorithms that people might want to use at the higher level to simulate problems. So for example, one very common problem in quantum physics and on quantum computers is you have a tensor network and you want to essentially apply a series of two-site gates to the network. So you imagine that you have a quantum processor and you want to apply a circuit involving two-site gates on certain pairs of qubits. And you can map this to taking a tensor network and trying to apply these two-site tensors to them. And so we offer a code essentially for doing this, for taking the tensor network, applying the gate, getting new tensors, truncating them, and the beauty is you can do it with the backend you want. You could ask for the exact backend and do a proper update with the exact correct environments coming from the rest of the network. You can ask for the belief propagation backend, and essentially you can do it under the approximation or under the method you want. And then we have very simple code. For example, say we wanted to do the dynamics of an Ising model, so just a series of interacting quantum spins on some square lattice, a Lie lattice, which is a square lattice with decorated edges. It really is as simple as you define the graph, then you define the initial tensor network based on that graph with all the spins pointing up. You define your Hamiltonian, and then you essentially, in this case I'm doing belief propagation, so you build your message tensors and then you just call the apply function. And this is doing sort of a time-evolving block decimation method on a fairly complicated model, and yet the code is incredibly simple to kind of use and read. We also offer, so one of the big algorithms for tensor networks is the density matrix renormalization group, which is essentially finding the lowest eigenvalues of matrix product operators or tensor network operators. So tensor networks that essentially you apply to other tensor networks. And we have code for doing this on any tree. So instead of just doing it on a matrix product state, you can now essentially choose your tree and find the ground state of some Hamiltonian, or just generally solve an eigenvalue problem in terms of that operator in that tensor network. And we're continuously trying to build up our suite of tools with this package and hoping to offer kind of more and more and a better and better user interface. And so kind of moving on from the code and the code design, I'm going to talk about a few applications that that are ongoing or that we've already done with this tensor network package. So last year, IBM published a paper in Nature essentially taking their quantum processor, which is this arrangement of 127 qubits that I've got over here in this kind of like hexagonal type graph, and they ran, essentially simulated a quantum problem on it in terms of the dynamics of some interacting spins. And what they showed was that when they compared it to certain tensor network methods or brute force methods, that their quantum computer was far more accurate than any of these methods, and so it led them to essentially claim their quantum computer was doing something useful that classical computers couldn't. And even the New York Times has got a lot of press attention and continues to. And essentially they are taking their quantum processor and they're applying a series of gates defined by this unitary propagator here on the processor. And so what we did when we saw this paper is thought, well, why don't we try it with our code? Why don't we just build a tensor network using our graph tools that looks exactly like the processor and just run the circuit on the tensor network? And that's exactly what we did. And it turns out that, for example, in regime where they kind of showed that tensor networks were failing, that with our tensor network we're able to essentially get the errors on the problem to be incredibly small. Here on the left, this is errors on the order of the machine precision, and it runs in 5 seconds. And then even for slightly harder problems, we get errors on the order of 10 to the minus 6, and it runs in a handful of minutes. And these are problems that they claimed even a supercomputer using other tensor network methods that they tried couldn't do. And then we kind of moved into a regime where the circuit was so deep there wasn't even any results to compare to. And we essentially converged our results and showed that they were highly accurate and that they performed much better than the other tensor network methods they tried, which were based on using either a one-dimensional matrix product state or using a two-dimensional tensor network that was incredibly hard to optimize. Rather than we optimized our tensor network that looked exactly like their processor and used belief propagation. And we get highly accurate results that go through the same results as the processor, except for this anomaly over here, this kind of black circle that lies off our curve, but we know that our curve is correct here, so that something's going wrong with the quantum processor. But yeah, so we get highly accurate results and with very simple code. And kind of following this, we also now actually really understand the physics of this problem that they simulated on their processor. You can actually write down a very simple model which effectively captures the dynamics of this system by understanding it in terms of a phenomenon called confinement, where excitations on this lattice are actually highly localized because of this potential that's created in the system. And we show that the kind of physics of this IBM experiment is entirely described within this framework, and you can kind of write down a simple model that matches the numerical data. And this kind of explains why a belief propagation method works so well, is because the system is so localized, the correlations don't go round the loops in the system. They stay too local for the size of the loop. So the system acts like a tree. And so when you run belief propagation, you get really accurate results. More recently, we've been starting to think about some other applications of our package. And one of these is mathematics with tensor networks. So this general idea that if you have a mathematical function, you take a continuous variable, you do a binary decomposition, then you can think of all the values, and that kind of creates a grid, a discrete grid of with an exponentially fine spacing, and you can think of trying to store all the values for that function, and it's going to be in this enormous tensor. And we're going to see what can certain functions be actually represented as tensor networks with polynomial resources, even though you're actually storing the whole function on some grid with an exponentially small grid space. And this is an idea that's been around kind of for the last 10 years and been shown to be applicable to things like trying to solve the Navier-Stokes equation with this method, or trying to do things like the Fourier transform or wavelet transforms. But all of these papers have all been in the context of essentially one-dimensional tensor networks. So using one-dimensional tensor networks to encode these functions. But that kind of implies that you're trying to you have to choose an ordering for your binary digits, and you say, okay, the most significant binary digit is the leftmost tensor, and the next one is the rightmost tensor, and so on down the one-dimensional chain. But then you start asking questions, well, what about multi-dimensional functions? What about more complex functions where maybe I don't want the digits to be ordered that way? And the idea that we have is by using I-tensor networks, we can leverage that degree of freedom and explore that degree of freedom. So we're essentially working on this passage, I-tensor numerical analysis, myself and my collaborators, which explores this degree of freedom and actually tries to write a Julia package which does mathematics within this tensor network framework, and you can choose whichever tensor network that you want and the kind of ordering of the digits that you want. So for example, the code looks something like this. Let's imagine that I have this complex function, z1q times z2 plus z2 squared times cos squared of pi z. Okay, so these are complex numbers. It's a function of 3 variables, and what you can do is you specify the number of digits that you want. So I'm gonna decompose these 3 continuous variables into 12 binary digits. I'm gonna try to represent it on a tree tensor network that looks like a little comb of sort of like dimension 1, dimension 2, dimension 3. And then you just construct it in the code like this, and it builds a tensor network that represents that function, and you can compare the values in that tensor network to the values of the exact function, and you get agreement to essentially within machine precision. So you can construct certain basis functions in this way, and that tensor network really is storing every single possible value of the function on this exponentially fine grid. So it's doing an incredibly large compression of this data. And the idea of this package is that then we will try to explore constructing more complex functions, solving differential equations, and essentially see how far that can take us. So for example, kind of a more complex function is, say, this function here, which is a 3-dimensional function which is the sum of a load of random plane waves, each with very different frequencies, so kind of integer frequencies, and then we benchmark representing the function with 3 different tensor networks here, 2 kind of 1-dimensional tensor network and 1 comb tensor network, which is the blue line. And you can see that when you compare to essentially the error from representing this function, so kind of the error between the values of the function that you have in your tensor network versus the actual values of the function versus sort of the bond dimension, so the rank between the tensors needed here, you find that when you use this comb tensor network, which is not 1-dimensional, you get a massive improvement, orders of magnitude in terms of error for a fixed memory cost. So actually moving away from 1D and trying to think about more general structures enables us to get some really powerful results and could allow us to actually deal with some much more complicated functions than can currently be dealt with. And then to kind of summarize where we're looking for the future is thinking about new features for the I-tensor networks library, thinking about corrections to first-order corrections to belief propagation, so that we can deal with sort of smaller loopy tensor networks but still do something much better than an exact contraction sequence. Building a density matrix renormalization group algorithm based on belief propagation so that it will work for loopy tensor networks. And then the idea would be to try to apply these methods to some very interesting problems in physics and more generally. So, for example, looking at 3-dimensional materials with 3-dimensional tensor networks, or doing quantum dynamic simulations of various physical phenomena and kind of thinking about the kind of quantum processes that are around, such as IBM's quantum processor, and matching our tensor networks to those processes, and then doing things like differential and integral equation solving with our numerical analysis package. So we have a lot of exciting things going on, and yeah, ideas for the future. So thank you very much for listening. These are some of my collaborators at the Flatiron and elsewhere. Yeah.
We have 1 minute for questions.
On your last slide, you mentioned a shibboleth that makes me very excited. What does it mean? First-order corrections for belief propagation that work on loopy networks?
Yeah, so essentially you can kind of think about belief propagation like sort of taking an edge of your network SVDing it down and like saying that it essentially just assumes that that SVD gives you like one dominant singular value that's 1 and all the rest is 0. And so the idea with exact contraction methods try to get that whole spectrum. They keep that whole spectrum, but typically that will decay fairly fast. So if we could just get a handful of those dominant singular vectors instead of just one of them, we could still have an algorithm that's polynomial time, but it can handle loopy networks to some fairly good accuracy, depending on the network and the problem. And I think that could open up a huge number of problems in quantum physics with classical methods that people kind of think can't be done, but actually with the right code and the right ideas, I think we can make a lot of progress.
And just to make sure I understand, this is correction to the contraction. It's not a general belief propagation.
Yeah, it's a correction to the contraction, so it's like a more accurate way of contracting it.
Thank you.
Okay, we don't have more time for questions. Thanks, Joseph. Also, just in case you didn't know, we're going to have Quantum Mini dinner together around 6 after the final talk, and come back to this room if you want to join around 6.
Configurations.jl?
Yes.
Yes, I use your package a lot. It's
Thanks.
awesome.
Thanks. What do you, so what you're, oh, you're from Asmal.
Yes,
Nice.
I work with Jorge, and he told me about your package.
Oh, cool.
It's like, I know that name. Thank you. Maybe I'll reach out to
So let's welcome our next talk about projector Monte Carlo. Let's welcome Joachim. I'm pronouncing correctly.
Joachim Brandt. Yeah, thank you very much. My name is Joachim Brandt. I'm going to talk about projector Monte Carlo and exact diagonalization with remu.jl. And there's a QR code with materials, both code and slides. All right, so just to make sure that I don't run out of time, I'd like to acknowledge here collaborators. Let me start at the beginning. So the research and also the code is inspired by Ali Alavi down here. So the picture is from a joint group photo during a sabbatical in Stuttgart. So Ali is, pioneered the method. So they're quantum chemists, and they use this as a quantum chemistry code to solve quantum chemistry problems. Now, what inspired me, and so here Elke is my lovely wife. So we thought about together, we want to actually apply this to more general problems that are not quantum chemistry. So quantum particles that can be bosons, fermions with different spins, mixtures. And we started writing our own code. And then later, a number of students and postdocs have contributed. In particular, I would like to point out Ray, Chris, and Mattia. And recently, Mattia has been doing really, really good work on the code. And some of the algorithmic things that I'll be presenting are basically his work. Okay, so we're based in New Zealand, far away. There's a map. We're part of a research center that's actually delocalized across the whole country, and Massey University is here on the outskirts. Our campus of Massey University is on the outskirts of Auckland in the far north. So what do we want to do? We want to solve a number of quantum mechanics related problems. We find, so the first and foremost is to find the ground state and low-lying excited states of a large quantum Hamiltonian. And here the emphasis is on quantum many-body problems, so the Hamiltonian is large. In principle, it's so large that we can't represent it. We can't even represent the eigenstates. So the previous talk tensor networks is one way of reducing this exponential complexity that we have. So we're going to do it with random numbers. So there are a number of other problems that we're actually also interested in, which is quantum dynamics, finite temperature physics, open quantum systems, and the references here all point to papers that have demonstrated that this can be done with the method, full configuration interaction quantum Monte Carlo, the flavor of projector quantum Monte Carlo that we're implementing, but they're not available in a single code. There are basically two open source Fortran codes that sort of implement this method, but they also have their limitations and are basically geared at quantum chemistry at dealing with problems with electrons. Now, what motivates us, particularly in my research here, is the physics of ultra-cold atoms and molecules. So you can build artificial quantum systems with that. So here's an example of a quantum gas microscope experiment. So there's lasers here manipulating, generating an optical lattice potential. After these atoms have been cooled to nanokelvin temperatures in some vacuum chamber, and then there's a very powerful microscope from the bottom that can resolve single site and single atom what these particles are doing, and their motion or their quantum states are fully quantum mechanical. So every time you photograph it, basically you take a quantum measurement of the position of these particles. So very impressive experimental progress, over the last few decades. Now, so what is REMU? Name of our package. REMU is a native tree of New Zealand. It's also on my shirt. Yeah. But yes, we've been using it as an acronym. Sorry if this is a little bit small. I'll read this out. Stands for Random Integrators for Many-Body Quantum Systems. So currently we're mostly implementing this full configuration interaction quantum Monte Carlo flavor of projector quantum Monte Carlo. But the idea is we want to be a bit more general and want to do more than that. Currently, what we're doing, what the code can do is interact with quantum many-body models. So we can, for example, do matrix-free exact diagonalization of quantum many-body models if they're specified in our in the interfaces that we've implemented. So we have a suite of quantum of basis states, of Fock states, slated determinants to represent these kinds of problems, and we have an interface for defining many-body Hamiltonians, and I'll show you some code examples later. Predefined examples here are Hubbard models, Hubbard-related lattice models, also transcorrelated Hamiltonians for contact interacting particles, quantum particles, as relevant for ultra-cold atoms, and then some statistical analysis. So why this particular flavor, full configuration interaction quantum Monte Carlo? So it goes back to publications from Alabi's research group in 2009. It's fairly recent, even though the idea of projector quantum Monte Carlo is actually very old. The first paper I found was from 1962. Kalos, Green's function, Monte Carlo, and then diffusion Monte Carlo came about a decade later, and then there are other flavors, auxiliary field and path integral ground state Monte Carlo, all trying to solve the same problem, basically a Hamiltonian that is way too large and you still want to find out what is the ground state energy or what are its properties. Now, what I like about the particular flavor here is that even though it was particularly developed for quantum chemistry problems, it's really just a stochastic extension of exact diagonalization. So you can anything that you can represent as a large sparse matrix basically you can throw at this method and it will tell you something about it. Right, so here are a few milestones. I don't need to go through all of it. It's just a few. So from 2009 on, there were some important developments, mostly by other people. Our modest contributions here are, in particular these two papers down here about modifying the algorithm to make it actually a little bit more convenient to control population, and then analysis of a population control bias that I will later show you in action, actually. Right, so starting point is a Fock space basis. So we have a many-body quantum state, psi naught, using physics notation here, and maybe we'll switch to more linear algebra notation later. So there's a coefficient vector, and there are basis states. So these basis states are Fock states. So here's an example of bosonic Fock states, but they could be, bosons, fermions, anything. One problem is, one particular problem that I'll show you examples with is the Bose-Hubbard model. It's represented in this very compact way, but it's basically just a recipe to calculate matrix elements from in this basis. And the matrix elements, they look like this formally, and then eventually you end up at a basis, at a matrix of numbers, but they're indexed now by these Fock states, and the Fock states are represented explicitly in the code. It's very sparse. Here's a sparsity pattern. So now, what do we do to find the ground state? So it's really a generic linear algebra problem, finding the lowest eigenpair of this matrix. So it can be solved with a variant of power iterations, which is applying this operator t, multiplying that repeatedly to some vector, some initial vector. And this transitional operator t is essentially, contains minus the Hamiltonian with some time step parameter. There's a scalar parameter s that we call it the shift. It's quite important. It has to be, we adjust it at every time step, because if we don't do this, this would be just exponentially growing or exponentially decaying. So we don't want that. Didn't write out the equation explicitly of how we do that. But if we do that to control the norm, then eventually this becomes a fixed point method, fixed point iterations, and it's easy to see that when this converges, that eventually the coefficient vector will be the exact eigenvector, and the scalar shift will converge to the ground state energy. Okay, so now there's a code example. Let me switch to this Jupyter Notebook. So here, let's go through the code a little bit. Already loaded the packages. Remo is a registered package. So how do we represent Fock states? So we use an occupation number basis. BoSFS stands for bosonic Fock state. This is just two bosons in the first mode, two bosons in the second mode, and so on. So these modes, they can represent, in this case here for Bose-Hubbard model, they will represent lattice positions, or they could be orbitals for chemistry-like problems. They're represented very compactly as bit strings internally. So specifically for these bosons with fixed particle number, we have an encoding that has to be read from right to left now. Two bosons, 0 marks the boundary to the next orbital or the next mode, two bosons in the next one, and then 1 and 1 boson, as you see it here. But we have a number of different ways of representing these efficiently. We also have a shortcut notation here, which we use for printing out, which is quite convenient. Just for an example, we have composite addresses here. So there are two fermion components. So this would be spin 1/2 fermions would be represented this way. again with a convenient shortcut notation. Now we have represented the basis states. So how do we store quantum states? In particular, we want to store them sparsely because we don't want to store all of it. So internally, this works with hash tables, with dictionaries. So this is so that we can, access the value of an address very quickly. Another way to do this would be to keep a sorted list, but that is very expensive if you scale it up. So this is quite convenient. And for addresses that have not been explicitly stored, this just returns 0. So conceptually this is a vector, but of course it's not a vector that it's not a vector in terms of Julia's vector definition. It's not an abstract vector. So now then, we have the quantum states. Now let's move to the Hamiltonians. We've defined an interface for abstract Hamiltonians, and it's fairly simple. So there are these functions, these methods here that you have to implement if you want to use that. Starting address basically defines the address space. Diagonal element, once you're given a Hamiltonian and an address, you need to be able to compute the diagonal element. Number of off-diagonals is the number of non-zero elements given an address that are in the column of the matrix of the Hamiltonian, and get off-diagonal is to access them. So that is all that is needed to define this Hamiltonian, and then there are a few optional methods that make working with it more convenient. And once you have that, you can do something like vector matrix multiplications. So here's an example. How does a Hubbard model in real space look like? It's defined by these equations. And so here we have something that is, this is our predefined method. Predefined model. And the nice thing is we can throw it at now address types of bosons or fermions or even composite particles. And whether it's a Bose-Hubbard model or a Fermi-Hubbard model will be decided by which type of address you pass in. And there's various geometries. So let's do this. Let's instantiate a Hamiltonian. This would be a Hubbard real space for a bosonic, the initial state that we defined earlier. So now we have that. We can calculate the diagonal element. Now it's very important, of course, because we'll be doing this, during the Monte Carlo algorithm again and again, that this is really efficient. So, and thanks to Julia's amazing capabilities of just-in-time compilation, this compiles down to very fast code. So you see it takes only a few nanoseconds to calculate the diagonal elements. Off-diagonal elements for this particular model take a little bit longer, 50 nanoseconds or so. But if you implement your own Hamiltonian, it's very important that that is done efficiently. Right. So the particular one that I've instantiated here is small enough that it can be represented as a sparse matrix. So this is implemented just by calling sparse, or can be converted into a matrix here. And now the nice thing is now you can start doing exact diagonalization, and you can just use Julia's linear algebra ecosystem to do linear algebra on it. However, we can also do matrix-free exact diagonalization, which is a very nice feature. And we didn't even have to implement that ourselves, but we're using an external package, KrylofKit. I just found that at some point, that this package exists. It implements the Lanczos algorithm for finding the ground state of a Hamiltonian. It doesn't know anything about our types. It's agnostic, but it doesn't require vectors to be abstract vectors and operators to be operators. It basically works with duck typing. So you could use the functions of Krylov-Kit directly themselves, or we've implemented here a nice interface inspired by the SciML way of doing things, defining this as an exact diagonalization problem where we just specify an algorithm which is a matrix-free Krylov-Kit solver, and then we call solve, and it will run the Lanczos algorithm, give us a result, and here we see what the eigenvector looks like. Right, so now let's do quantum Monte Carlo. This was just linear algebra so far, numerical linear algebra. So we instantiate a projector Monte Carlo problem, and you see it prints out with quite a lot of details. This is all the options that I didn't specify, but you can specify them as keyword arguments of specific algorithms that you want to use, for example, or time step details. I'm just using defaults here. So, and that can be solved and should run fairly quickly. Returns a simulation struct. Now we can extract a data frame from it, which gives us a time series. Yeah, we're stepping through, we're doing these iterative applications of the transition operator here. And then we can look at this by plotting the norm, for example. The norm is not held constant, but it's controlled by a parameter, which is called target Walker number. We've set this to 1,000. So there's a transient until the norm gets to where it should be, and then it just fluctuates around it. So if we look at the shift, you remember the shift is a parameter that converges to the exact ground state energy. Again, there's some transient, and then it will fluctuate around the exact ground state energy, which is exactly what it does. Compare it here to the exact energy that we've calculated previously with the Lanczos algorithm. Okay, so that works, but obviously this was a ridiculously small matrix. You wouldn't need quantum Monte Carlo for it. So let's do this with a larger Hilbert space. Here we have 20 bosons in 20 modes. And we instantiate a Hubbard model, Bose-Hubbard model with it. So now how large is this Hamiltonian? How large is the Hilbert space here? It's 7 times 10 to the 10. So that's already something that I wouldn't be able to just do by exact diagonalization on my laptop. Again, we instantiate a Monte Carlo problem, then we solve it, and this also runs very quickly. Again, we plot the norm. Here now we see it fluctuates around this 1,000 value of 1,000 that was given as a target. Also, the shift is very noisy, and for comparison, so it fluctuates. And for comparison, I've given here an estimated number of best value that we know about the ground state energy. You see that it fluctuates a little bit higher. So the important thing, of course, once you have results like that, is to do statistical data analysis on it. I mean, it's fairly simple for the energy. Really, you want to calculate the mean as an estimator, but then you want to know also, how accurate is that. And so this is done with a blocking analysis here that essentially removes correlations, autocorrelations in this time series. And that gives us a value and an error bar here. So this is plotted. In here, you see the value is quite a bit higher, and the error bar is the width of this bar here that we see. Okay, so what has happened? Now we didn't actually get the energy out that we wanted, that we were hoping for. The reason for is that there's a population control bias. It's a statistical bias that comes from the fact that we have such a lot of noise in the way we're doing things. So actually I was a little bit surprised when we first found this, because in the literature people don't mention this very much. But for this type of problem it turns up. Yeah, so it's something that has to be dealt with. On the other hand, there's a lot of experience on how to deal with it. Okay. Very well, I'll go quickly. So important sampling is the right way to do it. So this is implemented here with very simply with a wrapper of the Hamiltonian. It's a very simple way of doing important sampling. Now we solve it again. Plot the result. And you see that this is now much closer, has a smaller error bar. But you see also the numerical resources. All of this ran in real time on my laptop, are really small for this really large problem. If we use more walkers and more computer time, we will get more accurate results. Okay, let me quickly switch back here. Right, so the actual stochastic sampling procedure is, resembles mostly matrix vector multiplication with the additional step that we're stochastically compressing basically vectors twice. Once it is done on this column of the matrix, and once it is done on the final vector. And the stochastic compression removes a lot of the values by keeping the expectation value the same, but reducing the number of elements that we have to store. I don't have much time, so I don't want to go into too much detail on how we parallelize this, but we've worked out a way to parallelize this with threaded operations to avoid memory races. It's fairly efficient. We parallelize with MPI on HPC. This also works quite well. We distribute the vector, all the data actually across the different nodes of HPC and of our high performance supercomputer, and then use MPI in every time step to communicate things. So it took us a while how to figure out how to do this well. And recently, so these are I'm showing you the first benchmarks we've been doing on a really large computer. On Frontier is that. And you see there's a speed up from 20 nodes going to 160 nodes or so, which I guess could be improved. Blue here is really small Walker number. There it's not efficient, and it didn't make sense to distribute it really. But if you have 2 orders of magnitude larger number of Walkers, it starts making sense. Weak scaling benchmark here, we actually went to 1,000 nodes. So this runs now on 1,000 nodes on a large-scale supercomputer. Where we increase the number of walkers for the same problem, which basically increase the number of stored vector elements. So increasing that by 3 orders of magnitude, basically it slows down by a factor of 6, but it's still actually quite impressive. Right. So we can. So this is just to show that we can do large problems and find here an indicator of the Bose-Hubbard, the Mott-insulated superfluid phase transition in the Bose-Hubbard model. Dimension of Hilbert space here goes up to 10 to the 58. This is really large. Obviously, not all of this is really well needed for the calculation, otherwise it wouldn't work. Okay, I guess I'm at the end. So this is available right now. The rest is future. We're really excited to have collaborators, and I'll leave the funding slide up here while I'm done with the talk. Thank you for your attention.
still have 1 minute for questions. Any questions? Okay.
Yeah, so I'm just wondering about this interface, this Hamiltonian interface you're coming up with. I mean, your index is essentially quite rich. Like, you know, it has a lot of information about the structure of the system and so on and so forth. But if I'm like in a more traditional quantum chemistry, quantum physics setting, mean field, for example, I often just have a matrix. I just have an index, which is a number, right? Do you provide some support for easily going back? Right? Or is it something I would need to build up, like some mapping from basically the
So the index is the Fock state, right?
Yes.
Is the slated determinant.
Yes.
So we just need to know which orbitals are occupied, essentially.
Yes, but I would have to do that manually. So it would be my job to do that mapping.
Yeah, if you wanted to implement that, you would. Well, in fact, in principle, you can do it any way you like. You could use your own index if you know how to index into that Hamiltonian. It doesn't really matter. This is just the things that are provided.
Okay, so you're not determined on that particular type.
No. It's not necessary to use that interface, but if you have that and then you have a Hamiltonian that can be written down in second quantization, then you can use our very convenient methods to do that.
I mean, do we have more time? I have a follow-up. Do you have more time? I have a follow-up, but I can also...
But if anyone wants to go to the keynote talk, feel free to, I guess you can feel free to go. But technically, this is the...
We are also taking the picture right before the keynote, so if you want to be in the JuliaCon picture.
No, we have to run.
We don't have to.
All right,
Okay, maybe we can do that later, and we go to the picture so that we're in time.
All right. Thanks everyone coming for Quantum Mini. Just final reminder that we're going dinner together later after the keynote. Thank you.